1. Introduction to Linux Debugging. 1.1 Understanding the debugging process. Debugging is an essential skill for any Linux developer or system administrator. It is the process of identifying and fixing errors, bugs, and issues in software or systems. Debugging allows you to analyze and understand the behavior of your code or system, helping you to locate and resolve problems effectively. In Linux, the debugging process involves several steps that help you identify, isolate, and fix issues. Understanding these steps is crucial for mastering Linux debugging. Let's explore the debugging process in detail. 1. Identify the problem. The first step in the debugging process is to identify the problem. This involves understanding the symptoms, error messages, or unexpected behavior that you encounter. It is essential to gather as much information as possible to narrow down the scope of the issue. 2. Reproduce the problem. Once you have identified the problem, the next step is to reproduce it. Reproducing the problem helps you understand the conditions under which it occurs and allows you to isolate the issue. By replicating the problem, you can analyze the behavior and gather more information to aid in the debugging process. 3. Gather information. To effectively debug an issue, you need to gather relevant information. This includes error messages, log files, system configurations, and any other data that can provide insights into the problem. Gathering information helps you understand the context and aids in the analysis and resolution of the issue. 4. Analyze the code or system. Once you have gathered the necessary information, it's time to analyze the code or system. This involves examining the relevant sections of code, system logs, and configurations to identify potential causes of the problem. Analyzing the code or system helps you narrow down the root cause and develop a strategy for debugging. 5. Use debugging tools. Linux provides a wide range of debugging tools that can assist you in the debugging process. These tools help you monitor the execution of your code, track variables, analyze memory usage, and identify performance bottlenecks. Some common debugging tools in Linux include GDB, strace, ltrace, valgrind, and perf. Familiarizing yourself with these tools is essential for effective debugging. 6. Apply debugging techniques. Debugging techniques are strategies or approaches used to identify and fix issues. These techniques include step-by-step execution, breakpoints, logging, tracing, and code inspection. Applying the appropriate debugging techniques can help you narrow down the problem and locate the specific area of code or system that requires attention. 7. Test and verify fixes. Once you have identified and fixed the issue, it is crucial to test and verify the fixes. This involves running tests, performing regression testing, and ensuring that the problem no longer occurs. Testing and verifying fixes help you ensure that the issue has been resolved and that the code or system is functioning as expected. 8. Document the debugging process. Documenting the debugging process is essential for future reference and knowledge sharing. It helps you keep track of the steps taken, the analysis performed, and the solutions applied. Documenting the debugging process also enables you to create a knowledge base that can be shared with other developers or used as a reference for similar issues in the future. By following these steps and mastering the debugging process, you can effectively identify and resolve issues in your Linux code or system. Debugging is a skill that requires practice and experience, but with the right tools and techniques, you can become proficient in debugging Linux applications and systems. 1.2 Common debugging tools in Linux. Debugging is an essential part of the software development process. It helps developers identify and fix issues in their code, ensuring that the software functions as intended. In the Linux environment, there are several powerful debugging tools available that can assist developers in diagnosing and resolving problems efficiently. In this section, we will explore some of the most commonly used debugging tools in Linux. 1. GDB GNU Debugger. GDB, short for GNU Debugger, is a powerful command line tool that allows developers to analyze and debug their programs. It supports various programming languages, including C, C++, Python, and more. GDB provides a wide range of features, such as breakpoints, stepping through code, examining variables, and memory management. It also supports remote debugging, allowing developers to debug programs running on different machines. To use GDB, developers need to compile their code with debugging symbols enabled. This can be done by adding the G flag to the compiler command. Once the program is compiled with debugging symbols, it can be loaded into GDB for analysis and debugging. 2. Valgrind. Valgrind is a powerful debugging and profiling tool for Linux. It helps developers detect memory leaks, buffer overflows, and other memory-related errors in their programs. Valgrind works by running the program in a virtual environment and monitoring its memory usage. It provides detailed reports on memory errors, including the exact location in the code where the error occurred. Valgrind consists of several tools, including memcheck for memory debugging, cachegrind for cache profiling, and calgrind for call graph profiling. These tools can be used individually or in combination to analyze different aspects of the program's behavior. 3. Strace. Strace is a command line tool that allows developers to trace system calls and signals made by a program. It provides detailed information about the interactions between the program and the operating system, helping developers understand how the program behaves at the system level. Strace can be particularly useful for diagnosing issues related to file I/O, network communication, and process management. To use strace, developers simply need to run their program with the strace command followed by the program's executable name. Strace will then display a log of all system calls made by the program, along with relevant information such as arguments and return values. 4. ltrace. ltrace is a debugging tool that allows developers to trace library calls made by a program. It intercepts and records the dynamic library calls made by the program, providing insights into how the program interacts with shared libraries. ltrace can be useful for diagnosing issues related to library dependencies, function calls, and parameter passing. To use ltrace, developers need to run their program with the ltrace command followed by the program's executable name. ltrace will then display a log of all library calls made by the program, along with relevant information such as function names and arguments. 5. GDB server. GDB server is a remote debugging tool that allows developers to debug programs running on a remote machine. It works in conjunction with GDB, enabling developers to connect to a remote target and debug it as if it were running locally. GDB server is particularly useful for debugging embedded systems or programs running on remote servers. To use GDB server, developers need to start the target program with the GDB server command followed by the host and port number to listen on. On the host machine, GDB can then connect to the remote target using the target remote command, specifying the host and port number. Once connected, developers can use GDB's debugging features to analyze and debug the remote program. These are just a few of the many debugging tools available in the Linux environment. Each tool has its own strengths and focuses on different aspects of debugging. By familiarizing yourself with these tools and understanding their capabilities, you can become a proficient Linux debugger and effectively diagnose and resolve issues in your software. 1.3 Setting up the debugging environment. Setting up the debugging environment is an essential step in the debugging process. It involves configuring the necessary tools and resources to effectively debug Linux programs and system-level issues. In this section, we will explore the steps required to set up a robust debugging environment in Linux. Installing debugging tools. Before you can start debugging, you need to ensure that the necessary debugging tools are installed on your Linux system. Linux provides a wide range of debugging tools that can be used for different purposes. Some of the commonly used debugging tools include GDB New Debugger. GDB is a powerful command line debugger that allows you to analyze and debug programs written in various programming languages, including C, C++, Python, and more. To install GDB, you can use the package manager specific to your Linux distribution. For example, on Ubuntu, you can use the following command: sudo apt-get install GDB. SystemTap. SystemTap is a dynamic tracing tool that allows you to monitor and trace system activities in real time. It provides a scripting language that enables you to write custom probes to capture specific events and analyze system behavior. To install SystemTap, you can use the package manager specific to your Linux distribution. For example, on Fedora, you can use the following command: sudo dnf install systemtap. dtrace. dtrace is a dynamic tracing framework that originated in the Solaris operating system and has been ported to Linux. It provides a powerful set of tools and APIs for tracing and debugging system-level issues. To install dtrace, you can use the package manager specific to your Linux distribution. For example, on Oracle Linux, you can use the following command: sudo yum install dtrace utils. Valgrind. Valgrind is a memory debugging and profiling tool that helps you detect memory leaks, buffer overflows, and other memory-related issues in your programs. To install Valgrind, you can use the package manager specific to your Linux distribution. For example, on Arch Linux, you can use the following command: sudo pacman s valgrind. These are just a few examples of the debugging tools available in Linux. Depending on your specific debugging requirements, you may need to install additional tools or libraries. Configuring debug symbols. Debug symbols contain additional information about the program's source code, variables, and functions, which is essential for effective debugging. By default, when you compile a program, the compiler may strip away the debug symbols to reduce the size of the executable. However, for debugging purposes, it is important to have access to these symbols. To configure debug symbols, you need to recompile your program with the appropriate compiler flags. For example, if you are using the GCC compiler, you can use the G flag to include debug symbols. Here's an example command to compile a C program with debug symbols: gccgo my program, C. By including debug symbols, you enable the debugger to provide more detailed information during the debugging process, such as line numbers and variable values. Enabling core dumps. A core dump is a file that contains the memory image of a program at the time of its termination. It can be extremely useful for post-mortem debugging, as it allows you to analyze the state of the program and identify the cause of the crash. To enable core dumps in Linux, you need to adjust the system's core dump settings. By default, core dumps may be disabled or limited in size. To enable core dumps and set the maximum size, you can use the ulimit command. Here's an example command to enable unlimited core dumps: ulimit c unlimited. Once core dumps are enabled, whenever a program crashes, a core dump file will be generated in the current working directory. You can then use a debugger like GDB to analyze the core dump and investigate the cause of the crash. Using debugging environments. In addition to the command line debugging tools, there are also graphical debugging environments available for Linux. These environments provide a user-friendly interface and additional features to simplify the debugging process. One popular graphical debugging environment is Eclipse. Eclipse is an integrated development environment (IDE) that supports multiple programming languages and provides a powerful debugging interface. It allows you to set breakpoints, step through code, inspect variables, and analyze program flow. Another widely used graphical debugging environment is Code Blocks. Code Blocks is an open-source IDE that supports C, C++, and Fortran. It provides a user-friendly interface for debugging, including features like breakpoints, variable inspection, and call stack analysis. These are just a few examples of the graphical debugging environments available for Linux. Depending on your preferences and requirements, you can choose the one that best suits your needs. Conclusion. Setting up the debugging environment is a crucial step in the debugging process. By installing the necessary debugging tools, configuring debug symbols, enabling core dumps, and utilizing graphical debugging environments, you can create a robust and efficient debugging environment in Linux. With the right tools and resources in place, you will be well equipped to tackle any debugging challenge that comes your way. 1.4 Debugging Techniques and Strategies. Debugging is an essential skill for any Linux developer or system administrator. It involves identifying and fixing issues in software or systems to ensure they function correctly. In this section, we will explore various debugging techniques and strategies that can help you effectively troubleshoot and resolve problems in your Linux environment. 1.4.1 Understanding the debugging process. Before diving into specific debugging techniques, it's important to understand the overall debugging process. The debugging process typically involves the following steps. Reproduce the issue. The first step in debugging is to reproduce the issue or problem. This involves identifying the specific conditions or inputs that trigger the problem. By reproducing the issue, you can isolate the problem and understand its root cause. Gather information. Once you have reproduced the issue, it's important to gather as much information as possible about the problem. This includes collecting error messages, log files, and any other relevant data that can help in diagnosing the issue. Analyze the problem. With the gathered information, you can now analyze the problem to identify its root cause. This may involve examining code, system logs, or other diagnostic tools to pinpoint the source of the issue. Develop a hypothesis. Based on your analysis, you can develop a hypothesis about the cause of the problem. This hypothesis will guide your debugging efforts and help you formulate a plan to fix the issue. Test the hypothesis. Once you have a hypothesis, you can test it by implementing potential fixes or workarounds. This may involve modifying code, configuration settings, or system parameters to see if the problem is resolved. Verify the fix. After implementing a potential fix, it's important to verify that the issue has been resolved. This may involve retesting the system or application to ensure that the problem no longer occurs. Document the solution. Finally, it's crucial to document the debugging process and the solution you have implemented. This documentation will serve as a reference for future troubleshooting and help others who may encounter similar issues. 1.4.2 Common Debugging Techniques. Debugging in Linux involves a variety of techniques and tools. Here are some commonly used techniques that can help you effectively debug issues. Logging. Logging is a fundamental technique for debugging in Linux. By adding appropriate log statements in your code or system configuration, you can track the flow of execution and identify potential issues. Tools like syslog and journalctl can help you collect and analyze log messages. Debugging flags. Many software applications and libraries provide debugging flags that enable additional logging or diagnostic information. By enabling these flags, you can gain more insight into the internal workings of the software and identify potential issues. Tracing. Tracing involves monitoring the execution of a program or system to capture detailed information about its behavior. Tools like strace and ltrace can help you trace system calls and library calls, respectively, providing valuable information about the program's execution. Core dumps. Core dumps are snapshots of a program's memory at the time of a crash or abnormal termination. Analyzing core dumps can help you identify the cause of a crash and understand the state of the program at the time of the crash. Tools like GDB can be used to analyze core dumps. Profiling. Profiling involves measuring the performance of a program or system to identify bottlenecks or areas of inefficiency. Profiling tools like perf and gprofessor can help you identify hotspots in your code and optimize performance. Remote debugging. Remote debugging allows you to debug a program or system running on a remote machine. This can be useful when the issue occurs in a production environment or on a different machine. Tools like GDB Server and LLDB Server enable remote debugging. 1.4.3 Debugging Strategies. In addition to specific techniques, there are several general strategies that can help you approach debugging effectively. Isolate the problem. When debugging, it's important to isolate the problem and narrow down its scope. This involves identifying the specific component or subsystem that is causing the issue. By isolating the problem, you can focus your debugging efforts and avoid unnecessary distractions. Divide and conquer. Once you have isolated the problem, you can use the divide and conquer strategy to further narrow down the cause. This involves systematically disabling or removing components to identify the specific piece of code or configuration that is causing the issue. Use a systematic approach. Debugging requires a systematic approach to ensure that all possible causes are considered. This involves gathering information, analyzing the problem, and testing potential fixes in a structured manner. By following a systematic approach, you can avoid overlooking important details and increase the chances of finding a solution. Collaborate and seek help. Debugging can be a challenging task, and it's often helpful to collaborate with others or seek help from the community. Online forums, mailing lists, and developer communities can provide valuable insights and guidance when troubleshooting complex issues. Document and learn. Finally, it's important to document your debugging process and the solutions you have found. This documentation serves as a reference for future troubleshooting and helps you learn from your debugging experiences. By documenting your findings, you can build a knowledge base that can be shared with others and contribute to the overall improvement of the Linux debugging community. By understanding the debugging process, employing various debugging techniques, and following effective strategies, you can become proficient in debugging Linux systems and applications. Debugging is a skill that improves with practice, so don't be discouraged if you encounter challenging issues. With persistence and the right approach, you can overcome any debugging challenge and ensure the smooth operation of your Linux environment. 2. Debugging basic Linux programs. 2.1 Debugging C programs. Debugging C programs in Linux is a crucial skill for any developer working with the C programming language. Debugging allows you to identify and fix errors, understand program behavior, and optimize code performance. In this section, we will explore various techniques and tools available for debugging C programs in a Linux environment. Understanding the debugging process. The debugging process involves identifying and resolving issues in a program. It typically consists of the following steps. Reproducing the issue. The first step in debugging is to reproduce the problem or error. This involves running the program and observing its behavior to understand the issue. Identifying the cause. Once the issue is reproduced, the next step is to identify the root cause of the problem. This can be done by analyzing the program's code, examining error messages, and using debugging tools. Isolating the problem. After identifying the cause, it is important to isolate the problem area in the code. This helps in focusing the debugging efforts and avoiding unnecessary modifications to the program. Fixing the issue. Once the problem area is identified, the next step is to fix the issue. This may involve modifying the code, changing program logic, or applying patches. Testing and verification. After fixing the issue, it is essential to test the program thoroughly to ensure that the problem is resolved and that no new issues have been introduced. Common debugging tools in Linux. Linux provides a wide range of debugging tools that can help developers in identifying and resolving issues in C programs. Some of the commonly used tools are GDB New Debugger. GDB is a powerful command line debugger that allows you to analyze and debug C programs. It provides features like breakpoints, stepping through code, examining variables, and backtracing the program's execution. Valgrind. Valgrind is a dynamic analysis tool that helps in detecting memory leaks, buffer overflows, and other memory-related errors in C programs. It provides a suite of tools like memcheck, catchagrind, and massif, which can be used for different types of analysis. Address Sanitizer. Address Sanitizer is a memory error detector tool that is part of the LLVM compiler infrastructure. It helps in finding memory corruption bugs like buffer overflows, use after free, and heaped stack buffer overflows. Strace. Strace is a system call tracer that allows you to monitor the system calls made by a program. It can be used to debug issues related to file I/O, network communication, and process management. GDB Server. GDB Server is a remote debugging tool that allows you to debug a program running on a remote target machine. It enables you to connect GDB to a remote program and debug it as if it were running locally. Setting up the debugging environment. To effectively debug C programs in Linux, it is important to set up the debugging environment correctly. Here are some steps to follow. Compile with debug symbols. When compiling your C program, make sure to include debug symbols using the G flag. This will generate additional information in the executable file, which is required by the debugger to map the source code with the binary. Disable optimization. Disable any compiler optimizations using the O0 flag. Optimization can sometimes interfere with the debugging process by rearranging code or removing variables. Enable core dumps. Core dumps are files that contain the memory image of a crashed program. They can be analyzed later to understand the state of the program at the time of the crash. To enable core dumps, use the ulimit-c unlimited command. Use debugging tools. Install and familiarize yourself with the various debugging tools available in Linux, such as GDB, Valgrind, and Strace. These tools provide different capabilities and can be used in combination to effectively debug C programs. Debugging techniques and strategies. When debugging C programs in Linux, it is important to adopt effective techniques and strategies to efficiently identify and resolve issues. Here are some tips to consider. Start with a minimal test case. When encountering a bug, try to isolate it by creating a minimal test case that reproduces the issue. This helps in narrowing down the problem area and makes it easier to debug. Use print statements. Inserting print statements at strategic points in the code can help in understanding the program's flow and identifying the cause of the issue. Print statements can be used to display variable values, function calls, and other relevant information. Step through the code. Use the debugging tool's stepping feature to execute the program line by line. This allows you to observe the program's behavior and identify any unexpected or incorrect results. Inspect variables and memory. Use the debugging tool to inspect the values of variables and memory locations. This can help in identifying incorrect values, uninitialized variables, and memory-related issues. Analyze core dumps. If the program crashes, analyze the core dump file using the debugging tool. This can provide valuable information about the state of the program at the time of the crash, such as the call stack and variable values. By following these techniques and utilizing the available debugging tools, you can effectively debug C programs in a Linux environment. Debugging is an iterative process, and with practice, you will become more proficient in identifying and resolving issues in your C programs. 2.2 Debugging Shell Scripts. Shell scripts are an essential part of Linux systems, allowing users to automate tasks and execute commands in a sequence. However, like any other program, shell scripts can have bugs and errors that need to be debugged. In this section, we will explore various techniques and tools for debugging shell scripts in Linux. Understanding shell script debugging. Debugging shell scripts involves identifying and fixing errors or unexpected behavior in the script's execution. This process typically involves tracing the flow of the script, identifying variables and their values, and pinpointing the exact location of the error. Shell scripts can have various types of errors, including syntax errors, logical errors, and runtime errors. Syntax errors occur when the script violates the rules of the shell scripting language, such as missing or misplaced characters. Logical errors occur when the script does not produce the expected output due to incorrect logic or algorithm. Runtime errors occur when the script encounters issues during execution, such as accessing undefined variables or files. Debugging techniques for shell scripts. 1. Adding debugging statements. One of the simplest and most effective techniques for debugging shell scripts is to add debugging statements throughout the script. These statements can be used to print the values of variables, display the execution flow, or provide information about the script's progress. For example, you can use the echo command to print the values of variables at specific points in the script. By examining the output, you can identify any unexpected values or inconsistencies that may be causing the error. 2. Using the X option. The shell provides a built-in option, X, which enables debugging mode. When this option is used, the shell prints each command before executing it, along with the expanded values of variables. This can be helpful in understanding the flow of the script and identifying any issues. To enable debugging mode for a shell script, you can either add set X at the beginning of the script or run the script with the X option, like bash x script.sh. 3. Tracing execution flow. Tracing the execution flow of a shell script can help identify the exact location where an error occurs. This can be done by adding set E at the beginning of the script, which causes the script to exit immediately if any command fails. Additionally, you can use the set O or exit option to achieve the same behavior. Another useful technique is to use the set O X trace option, which prints each command before executing it, similar to the X option. This can provide detailed information about the execution flow and help pinpoint the error. 4. Debugging with shell check. Shell check is a powerful static analysis tool for shell scripts that can help identify common errors and best practices. It checks for syntax errors, variable misuse, and other potential issues in the script. To use shell check, you can install it using your package manager and run it against your shell script. It will provide detailed feedback and suggestions for improving your script's quality and reliability. Debugging tools for shell scripts. 1. Bash debugger (BashDB). Bash debugger, also known as BashDB, is a command line debugger specifically designed for shell scripts. It allows you to set breakpoints, step through the script's execution, and examine variables and their values. To use BashDB, you need to install it on your system and run your shell script with the BashDB command followed by the script's name. This will start the debugger and allow you to interactively debug your script. 2. Shell check. As mentioned earlier, shell check is not only a static analysis tool but also a helpful debugging tool. It can detect common errors and provide suggestions for improving your shell script's quality. To use shell check for debugging, you can run it against your script and carefully review the output. It will highlight potential issues and provide explanations and recommendations for fixing them. 3. Debugging with print statements. Adding print statements to your shell script can be an effective way to debug issues. By strategically placing print statements at different points in the script, you can track the flow of execution and identify any unexpected behavior. Print statements can be as simple as using the echo command to display the values of variables or more complex, such as using the printf command to format and display information. Conclusion. Debugging shell scripts in Linux is an essential skill for any Linux user or system administrator. By understanding the debugging process, using appropriate techniques, and leveraging debugging tools, you can effectively identify and fix errors in your shell scripts. Whether it's adding debugging statements, using the X option, or utilizing specialized tools like bashdb and shellcheck, the ability to debug shell scripts will greatly enhance your Linux troubleshooting skills. 2.3 Debugging Python scripts. Python is a popular programming language known for its simplicity and readability. It is widely used for various purposes, including web development, data analysis, and automation. Like any other programming language, Python scripts can have bugs and errors that need to be debugged. In this section, we will explore different techniques and tools available for debugging Python scripts in a Linux environment. Understanding Python debugging. Debugging is the process of identifying and fixing errors or bugs in a program. It involves analyzing the code, identifying the cause of the issue, and making the necessary changes to resolve it. Python provides several built-in tools and techniques that can help in the debugging process. Using print statements. One of the simplest and most commonly used debugging techniques in Python is using print statements. By strategically placing print statements in your code, you can track the flow of execution and observe the values of variables at different points. This can help you identify where the issue is occurring and what values are causing the problem. For example, if you have a function that is not returning the expected result, you can add print statements to display the intermediate values and check if they are correct. By printing the values of variables or expressions, you can gain insights into the state of your program and narrow down the source of the bug. Using the PDB module. Python also provides a built-in module called PDB, Python Debugger, that allows you to debug your code interactively. The PDB module provides a set of commands that you can use to step through your code, set breakpoints, and inspect variables. To use the PDB module, you need to import it into your script and then set a breakpoint at the desired location in your code. A breakpoint is a specific point in your code where the debugger will pause the execution and allow you to interactively debug. Once the breakpoint is set, you can run your script, and when the execution reaches the breakpoint, it will pause, and you can start debugging. You can use commands like next to execute the next line of code, step to step into a function call, and print to display the value of a variable. The PDB module also provides other useful commands, such as continue to resume execution, break to set additional breakpoints, and quit to exit the debugger. Using IDEs and text editors. Integrated development environments, IDEs, and text editors with Python support often come with built-in debugging capabilities. These tools provide a graphical interface for debugging, making it easier to set breakpoints, inspect variables, and step through the code. Popular IDEs like PyCharm, Visual Studio Code, and Eclipse PyDev have powerful debugging features that allow you to debug Python scripts efficiently. These tools provide a user-friendly interface with features like variable watches, call stacks, and breakpoints management. If you prefer using a text editor, some editors like Sublime Text, Atom, and Vim have plugins or extensions that provide debugging functionality. These plugins integrate with the Python debugger and provide a similar debugging experience as IDEs. Using external debuggers. In addition to the built-in debugging tools, there are also external debuggers available for Python that offer advanced features and capabilities. One such debugger is PDB++, which is an enhanced version of the built-in PDB module. PDB++ provides additional features like syntax highlighting, tab completion, and better command line interface. It also supports remote debugging, allowing you to debug Python scripts running on a remote machine. Another popular external debugger is PyCharm Debugger, which is part of the PyCharm IDE. PyCharm Debugger offers a comprehensive set of debugging features, including breakpoints, variable inspection, and step-by-step execution. It also supports remote debugging and can be used with both local and remote Python scripts. Conclusion. Debugging Python scripts in a Linux environment is an essential skill for any Python developer. By using techniques like print statements, the PDB module, IDEs, and external debuggers, you can effectively identify and fix bugs in your Python code. Remember that debugging is a process that requires patience and systematic analysis of the code. With practice and experience, you will become proficient in debugging Python scripts and be able to write more reliable and error-free code. 2.4 Debugging Java programs. Java is a popular programming language used for developing a wide range of applications, from desktop software to web applications and mobile apps. Debugging Java programs in a Linux environment can be a challenging task, but with the right tools and techniques, it becomes much easier to identify and fix issues. Understanding Java debugging. Debugging Java programs involves identifying and resolving errors, exceptions, and other issues that may occur during the execution of the code. The goal is to locate the root cause of the problem and make the necessary changes to fix it. Debugging is an essential part of the software development process, as it helps developers ensure the correctness and reliability of their code. Common Java debugging tools. There are several tools available for debugging Java programs in Linux. Here are some of the most commonly used ones. Java Debugger (JDB). This is a command line tool provided by the Java Development Kit (JDK) for debugging Java programs. It allows you to set breakpoints, step through the code, inspect variables, and evaluate expressions. Integrated development environments IDEs like Eclipse, IntelliJ IDEA, and NetBeans provide powerful debugging features that make it easier to debug Java programs. These IDEs offer a graphical interface for setting breakpoints, stepping through the code, and inspecting variables. Logging frameworks. Logging frameworks like Log4j and SLF4j can be used to log information, warnings, and errors during the execution of a Java program. By analyzing the logs, you can identify and debug issues in your code. Profiling tools. Profiling tools like Java Visual VM and your kit can be used to analyze the performance of a Java program. These tools provide insights into memory usage, CPU usage, and other performance metrics, helping you identify and optimize performance bottlenecks. Debugging Java programs with JDB. The Java Debugger (JDB) is a command line tool that comes bundled with the JDK. It provides a simple and effective way to debug Java programs in a Linux environment. Here are some basic steps to debug a Java program using JDB. Compile the Java program with debugging information. Before you can debug a Java program, you need to compile it with debugging information. This can be done by adding the G flag to the javac command. For example, javac g my program, Java. Start the Java program in debug mode. To start the Java program in debug mode, you need to use the JDB command followed by the name of the compiled class file. For example, JDB my program. Set breakpoints. Once the program is running in debug mode, you can set breakpoints at specific lines of code using the stop at command. For example, stop at my program, Java, 10. Start the program execution. To start the execution of the program, use the run command. The program will stop at the first breakpoint encountered. Step through the code. You can step through the code using commands like step, next, and cont. The step command allows you to step into a method, while the next command allows you to step over a method. The cont command continues the execution until the next breakpoint is encountered. Inspect variables. You can inspect the values of variables using the print command. For example, print variable name will display the value of the variable. Exit the debugger. To exit the debugger, use the quit command. Debugging Java programs with IDEs. Integrated development environments IDEs provide a more user-friendly and feature-rich debugging experience for Java programs. Here are some general steps to debug a Java program using an IDE. Import the Java project. Start by importing the Java project into your IDE. This can usually be done by selecting the project directory or importing the project from a version control system. Set breakpoints. Set breakpoints at specific lines of code by clicking on the line number in the IDE. This will pause the program execution when the breakpoint is reached. Start the program in debug mode. Run the program in debug mode by clicking on the debug button or selecting the debug option from the IDE's menu. Step through the code. Use the step into, step over, and step out buttons in the IDE to navigate through the code. These buttons allow you to step into a method, step over a method, or step out of a method, respectively. Inspect variables. The IDE provides a variable viewer that allows you to inspect the values of variables at any point during the program execution. Simply hover over a variable to see its current value. Analyze stack traces. If an exception occurs during the program execution, the IDE will display a stack trace that shows the sequence of method calls leading up to the exception. This can help you identify the cause of the exception. Use other debugging features. IDEs often provide additional debugging features like watch expressions, conditional breakpoints, and code stepping options. Explore these features to enhance your debugging experience. Conclusion. Debugging Java programs in a Linux environment can be done using tools like JDB or integrated development environments IDEs such as Eclipse or IntelliJ IDEA. These tools provide features like setting breakpoints, stepping through the code, inspecting variables, and analyzing stack traces. By mastering the art of debugging Java programs, you can effectively identify and fix issues, ensuring the reliability and correctness of your software. 3. Debugging system-level issues. 3.1 Debugging kernel issues. Debugging kernel issues in Linux can be a challenging task due to the complexity and critical nature of the kernel code. Kernel issues can cause system crashes, performance degradation, and other system-level problems. In this section, we will explore various techniques and tools that can help you debug kernel issues effectively. Understanding kernel debugging. Kernel debugging involves identifying and fixing issues within the Linux kernel. These issues can range from device driver problems to system crashes. To effectively debug kernel issues, it is essential to have a good understanding of the kernel's internal workings and the tools available for debugging. The Linux kernel provides several mechanisms for debugging, including kernel logs, kernel debugging options, and kernel debugging tools. These tools allow you to trace the execution flow, analyze kernel data structures, and identify the root cause of the problem. Enabling kernel debugging. Before you can start debugging kernel issues, you need to enable kernel debugging options during the kernel compilation process. These options include config_debug_kernel, config_debug_info, and config_kgdb. Enabling these options provides additional debugging information and enables kernel debugging features. Once you have a kernel with debugging options enabled, you can use various techniques and tools to debug kernel issues. Kernel debugging techniques. Kernel logs. Kernel logs are a valuable source of information for debugging kernel issues. The kernel logs contain messages generated by the kernel during its operation, including error messages, warnings, and debugging information. You can access the kernel logs using the dmesg command or by reading the /var/log/kern.log file. When debugging kernel issues, it is essential to carefully analyze the kernel logs for any error messages or warnings that may indicate the cause of the problem. The logs can provide valuable insights into the system's behavior and help identify the root cause of the issue. Kernel debugging tools. Linux provides several powerful tools for debugging kernel issues. These tools allow you to analyze the kernel's internal state, trace the execution flow, and inspect kernel data structures. Some of the commonly used kernel debugging tools include GDB. The new debugger, GDB, can be used to debug the Linux kernel. GDB allows you to set breakpoints, examine kernel data structures, and step through the kernel code. It provides a powerful command line interface for debugging kernel issues. Kdump. Kdump is a kernel crash dumping mechanism that captures the kernel's memory image when a crash occurs. This memory image can be analyzed offline using tools like Crash or GDB to identify the cause of the crash. SystemTap. SystemTap is a dynamic tracing tool that allows you to trace the execution of the Linux kernel and analyze its behavior. SystemTap provides a scripting language that allows you to write custom probes to trace specific kernel events and collect data for analysis. ftrace. ftrace is a built-in tracing framework in the Linux kernel that allows you to trace the execution flow of the kernel code. ftrace provides various tracing options, including function tracing, event tracing, and stack tracing, which can help identify performance bottlenecks and debug kernel issues. Kprobes. Kprobes is a kernel debugging feature that allows you to dynamically insert breakpoints into the kernel code. Kprobes can be used to trace the execution flow, collect data, and analyze the behavior of the kernel. Kernel debugging strategies. When debugging kernel issues, it is essential to follow a systematic approach to identify and fix the problem. Here are some strategies that can help you debug kernel issues effectively. Reproduce the issue. Try to reproduce the issue consistently to understand its behavior and identify the steps to trigger it. Reproducing the issue in a controlled environment can help isolate the problem and make it easier to debug. Analyze kernel logs. Carefully analyze the kernel logs for any error messages or warnings that may indicate the cause of the problem. Look for patterns or specific events that occur before the issue happens. Use debugging tools. Utilize the available kernel debugging tools like GDB, Kdump, SystemTap, ftrace, and Kprobes to trace the execution flow, analyze kernel data structures, and collect data for analysis. These tools can provide valuable insights into the kernel's behavior and help identify the root cause of the issue. Isolate the problem. If possible, try to isolate the problem by disabling or removing unnecessary kernel modules or hardware components. This can help identify if the issue is caused by a specific module or hardware interaction. Experiment and test. Experiment with different configurations, parameters, or patches to see if they have any impact on the issue. Testing different scenarios can help narrow down the possible causes and identify potential solutions. Collaborate and seek help. If you are unable to identify the root cause of the issue, don't hesitate to seek help from the Linux kernel community or forums. Collaborating with others who have experience in kernel debugging can provide valuable insights and help resolve the problem. Conclusion. Debugging kernel issues in Linux requires a good understanding of the kernel's internal workings and the tools available for debugging. By carefully analyzing kernel logs, using debugging tools, and following a systematic approach, you can effectively identify and fix kernel issues. Remember to reproduce the issue, analyze the logs, use debugging tools, isolate the problem, experiment and test, and seek help when needed. With these techniques and strategies, you can become proficient in debugging kernel issues and ensure the stability and performance of your Linux system. 3.2 Debugging device drivers. Device drivers play a crucial role in the functioning of a Linux system. They are responsible for facilitating communication between the operating system and hardware devices. However, like any other software component, device drivers can have bugs and issues that need to be debugged. In this section, we will explore the process of debugging device drivers in Linux. Understanding device driver debugging. Debugging device drivers can be challenging due to their low-level nature and direct interaction with hardware. Device drivers are typically written in C or C++, and they operate in kernel space, which means they have direct access to system resources and hardware. This low-level nature makes debugging device drivers more complex than debugging user space applications. When debugging device drivers, it is essential to have a good understanding of the driver's code, the hardware it interacts with, and the Linux kernel's internal workings. Device driver bugs can manifest in various ways, such as system crashes, device malfunctions, or unexpected behavior. Therefore, it is crucial to have a systematic approach to debugging device drivers. Debugging techniques for device drivers. 1. Kernel logs and debug messages. The Linux kernel provides various mechanisms for logging and debugging. One of the most common techniques is using printk statements to print debug messages to the kernel log. These messages can provide valuable information about the driver's execution flow, variable values, and error conditions. By strategically placing print case statements in the driver's code, you can trace the driver's execution and identify potential issues. 2. Kernel debuggers. Kernel debuggers, such as KGDB and KDB, allow developers to debug device drivers directly in the kernel space. These debuggers provide features like breakpoints, stepping through code, and inspecting variables. Using a kernel debugger requires setting up a debugging environment and attaching the debugger to the running kernel. While kernel debuggers can be powerful tools, they require a good understanding of the Linux kernel's internal workings and can be complex to set up. 3. Dynamic debugging techniques. Dynamic debugging techniques involve modifying the behavior of the running kernel or device driver temporarily to gather additional information. One such technique is using kernel probes, which allow you to insert custom code into the kernel or device driver without modifying the source code. Kernel probes can be used to trace function calls, monitor variable values, and capture specific events. Another dynamic debugging technique is using kernel trace points, which are predefined locations in the kernel code where you can collect trace data. Trace points provide a lightweight and efficient way to gather information about the driver's execution without significantly impacting performance. 4. Hardware debugging tools. In some cases, device driver issues may be related to hardware interactions. Hardware debugging tools, such as JTAG debuggers or logic analyzers, can be used to analyze the communication between the device driver and the hardware device. These tools allow you to monitor signals, capture data transfers, and identify potential hardware-related issues. Debugging workflow for device drivers. When debugging device drivers, it is essential to follow a systematic workflow to efficiently identify and resolve issues. Here is a suggested debugging workflow for device drivers. Reproduce the issue. Start by reproducing the issue consistently. Identify the specific conditions or actions that trigger the problem. This step is crucial as it allows you to isolate the issue and focus your debugging efforts. Enable debugging. Enable debug messages and logging in the device driver code. Use print case statements or other logging mechanisms to capture relevant information during the driver's execution. Analyze kernel logs. Examine the kernel logs to identify any error messages, warnings, or unexpected behavior related to the device driver. Look for patterns or specific events that may provide clues about the issue. Inspect driver code. Review the device driver's source code to understand its logic and identify potential areas of concern. Pay attention to error handling, resource allocation, and interactions with hardware devices. Use debugging tools. Utilize kernel debuggers, dynamic debugging techniques, or hardware debugging tools to gather additional information about the driver's execution. Set breakpoints, trace function calls, monitor variable values, or capture trace data to narrow down the problem. Isolate the issue. Once you have gathered enough information, try to isolate the issue further. Disable or modify specific parts of the driver's code to identify the root cause of the problem. Use a binary search approach to narrow down the problematic code section. Fix the issue. Once you have identified the root cause, fix the issue in the device driver's code. Test the fix thoroughly to ensure it resolves the problem without introducing new bugs. Verify the fix. Validate the fix by testing the device driver under various scenarios and conditions. Ensure that the issue no longer occurs and that the driver functions correctly. Document the debugging process. Document the debugging process, including the steps taken, the issues encountered, and the solutions implemented. This documentation will be valuable for future reference and for sharing knowledge with other developers. By following a structured debugging workflow and utilizing appropriate debugging techniques, you can effectively identify and resolve issues in device drivers running on Linux systems. Conclusion. Debugging device drivers in Linux requires a systematic approach and a good understanding of the driver's code, hardware interactions, and the Linux kernel's internal workings. By using techniques such as kernel logs, kernel debuggers, dynamic debugging, and hardware debugging tools, you can efficiently identify and resolve issues in device drivers. Following a structured debugging workflow helps ensure a systematic and effective debugging process. 3.3 Debugging System Services. System services play a crucial role in the overall functioning of a Linux system. These services are responsible for managing various aspects of the operating system, such as network connectivity, file sharing, printing, and more. When issues arise with system services, it can have a significant impact on the overall stability and performance of the system. Therefore, it is essential to have effective debugging techniques in place to identify and resolve these issues promptly. Understanding system services. System services are background processes that run continuously on a Linux system. They provide specific functionality and are typically started during the system boot process. Examples of system services include the Network Time Protocol (NTP) service, the Apache Web Server, the Secure Shell (SSH) service, and the Domain Name System (DNS) service. When a system service encounters an error or behaves unexpectedly, it can lead to various problems. These problems may manifest as service failures, slow response times, or even system crashes. To effectively debug system service issues, it is crucial to understand the underlying architecture and how these services interact with other components of the system. Logging and error messages. One of the primary sources of information when debugging system services is the system logs. Linux systems maintain various log files that record important events and error messages. These logs can provide valuable insights into the behavior of system services and help identify the root cause of any issues. The most commonly used log file for system services is the var log messages file. This file contains a wide range of system messages, including those generated by system services. By examining this file, you can often find error messages or warnings related to the service in question. In addition to the system log, many system services also have their own dedicated log files. These files are typically located in the var log directory and are named after the service they belong to. For example, the Apache web server logs can be found in var log httpd, while the SSH service logs are located in var log secure. When debugging system service issues, it is essential to carefully analyze the log files for any relevant error messages or warnings. These messages can provide valuable clues about the nature of the problem and help guide the debugging process. Service configuration. System services often have configuration files that control their behavior. These configuration files specify various settings and parameters that determine how the service operates. When debugging system service issues, it is crucial to review and verify the configuration settings to ensure they are correct. The location of the configuration files varies depending on the service. Common locations include etc. and etc. sysconfig. For example, the configuration file for the Apache web server is typically located at /etc/httpd/httpd.conf, while the configuration file for the SSH service can be found at etc. sshd_config. When reviewing the configuration files, pay close attention to any settings that may be relevant to the issue at hand. For example, if a service is not starting correctly, check the configuration file for any incorrect paths or missing dependencies. Similarly, if a service is experiencing performance issues, review the configuration settings related to resource allocation and tuning. Service dependencies. System services often rely on other services or components to function correctly. When debugging system service issues, it is essential to consider these dependencies and ensure that all required components are present and functioning properly. To identify service dependencies, refer to the documentation or official resources for the specific service in question. These resources typically provide information about the required dependencies and any additional configuration steps that may be necessary. In some cases, a service may fail to start or function correctly due to a missing or misconfigured dependency. By identifying and resolving these dependencies, you can often resolve the issue with the affected service. Process monitoring and debugging. When debugging system service issues, it can be helpful to monitor the running processes associated with the service. This can provide insights into the behavior of the service and help identify any abnormal or unexpected activity. The PS command is a useful tool for monitoring processes on a Linux system. By using the appropriate options, you can filter the output to display only the processes associated with a specific service. For example, to monitor the Apache web server processes, you can use the command psaux grep httpd. Once you have identified the relevant processes, you can use other debugging tools, such as strace or GDB, to further investigate the behavior of the service. These tools allow you to trace system calls, monitor signals, and even attach to running processes for live debugging. Conclusion. Debugging system services in Linux requires a systematic approach and a good understanding of the underlying architecture. By leveraging system logs, reviewing configuration files, considering service dependencies, and monitoring processes, you can effectively identify and resolve issues with system services. Remember to consult the documentation and official resources for the specific service in question, as they often provide valuable insights and troubleshooting guidance. With the right tools and techniques, you can ensure the smooth operation of system services and maintain the overall stability and performance of your Linux system. 3.4 Debugging network issues. Debugging network issues in Linux can be a challenging task, as there are numerous components involved in the networking stack. From the network interface cards (NICs) to the network protocols and services, any misconfiguration or malfunction can lead to connectivity problems. In this section, we will explore some common network issues that can occur in a Linux system and discuss various techniques and tools to debug them effectively. Understanding network issues. Network issues can manifest in different ways, such as slow or intermittent connectivity, inability to establish connections, or unexpected behavior in network-dependent applications. Before diving into the debugging process, it is crucial to understand the underlying causes of these issues. Here are some common network problems you may encounter. Misconfigured network settings. Incorrect IP address, subnet mask, gateway, or DNS server settings can prevent proper network communication. Firewall and security settings. Overly restrictive firewall rules or misconfigured security settings can block network traffic and cause connectivity problems. Network hardware failures. Faulty network cables, switches, or routers can disrupt network connectivity. Network congestion. High network traffic or bandwidth limitations can result in slow or intermittent connectivity. DNS resolution issues. Problems with DNS servers or misconfigured DNS settings can prevent proper name resolution, leading to connection failures. Routing issues. Incorrect routing tables or misconfigured routing protocols can cause packets to be sent to the wrong destination or dropped altogether. Network service failures. Malfunctioning network services, such as DHCP, DNS, or NTP, can disrupt network connectivity. Debugging network issues. When faced with network issues, it is essential to follow a systematic approach to identify and resolve the problem. Here are some steps you can take to debug network issues in Linux. Check network configuration. Verify the network settings, including IP address, subnet mask, gateway, and DNS server configurations. Use the ifconfig or ip command to view and modify network interface settings. Test connectivity. Use tools like ping or traceroute to test connectivity to other hosts or network devices. This can help identify if the issue is specific to a particular host or affects the entire network. Check firewall settings. Review the firewall rules and ensure that they are not blocking the required network traffic. Use tools like IP tables or firewall-d to manage firewall settings. Inspect network traffic. Analyze network traffic using packet capture tools like TCPdump or Wireshark. This can help identify any abnormal or unexpected network behavior. Check network hardware. Verify the physical connections, such as network cables and switches, to ensure they are functioning correctly. Replace any faulty hardware if necessary. Investigate DNS issues. Use tools like NSLookup or dig to troubleshoot DNS resolution problems. Check the DNS server configurations and ensure they are reachable and functioning correctly. Examine routing tables. Inspect the routing tables using the root command to ensure they are correctly configured. Identify any incorrect or missing routes that may be causing connectivity issues. Test network services. Verify the functionality of network services like DHCP, DNS, or NTP. Use tools like NSLookup or NTPdate to test DNS and NTP server connectivity. Monitor network performance. Use tools like iftop or nload to monitor network bandwidth usage and identify any congestion or performance issues. Debug network protocols. If the issue is specific to a particular network protocol, such as TCP or UDP, use protocol-specific debugging tools like TCPdump or SS to analyze the protocol-level traffic. Debugging tools for network issues. Linux provides a wide range of tools and utilities to assist in debugging network issues. Here are some commonly used tools. Ping, a basic tool to test network connectivity by sending ICMP echo requests to a target host. Traceroute traces the route packets take from the source to the destination, helping identify network hops and potential bottlenecks. TCPdump, a powerful packet capture tool that allows you to capture and analyze network traffic in real time. Wireshark, a graphical packet capture and analysis tool that provides a detailed view of network traffic. Netstat displays network statistics and active network connections, helping identify open ports and established connections. SS, a replacement for Netstat that provides more detailed information about network connections and sockets. ifconfig ip, used to configure and display network interface settings, including IP addresses, subnet masks, and more. IP tables firewall-d, tools for managing firewall rules and settings. NSLookup dig, DNS lookup tools that help troubleshoot DNS resolution issues. Route displays and modifies the routing tables, allowing you to manage network routes. By utilizing these tools and following a systematic approach, you can effectively debug and resolve network issues in a Linux system. Remember to document your findings and steps taken during the debugging process for future reference. Debugging network issues requires a combination of technical knowledge, troubleshooting skills, and familiarity with the Linux networking stack. With practice and experience, you can become proficient in identifying and resolving network problems, ensuring smooth and reliable network connectivity in your Linux environment. 3.5 Debugging file system issues. File system issues can be a common source of problems in Linux systems. These issues can range from file corruption and data loss to slow performance and unresponsive file operations. In this section, we will explore various techniques and tools for debugging file system issues in Linux. Understanding file systems in Linux. Before diving into debugging file system issues, it is important to have a basic understanding of how file systems work in Linux. Linux supports a variety of file systems, including ext4, XFS, BTRFs, and more. Each file system has its own set of features and characteristics, but they all serve the same purpose of organizing and managing data on storage devices. File systems consist of several components, including the superblock, inode table, data blocks, and directory structure. The superblock contains metadata about the file system, such as the total number of blocks, the block size, and the location of the inode table. Inodes are data structures that store information about files and directories, such as permissions, timestamps, and file size. Data blocks store the actual file data, while the directory structure maintains the hierarchy of files and directories. Common file system issues. File system issues can manifest in various ways, and it is important to identify the root cause of the problem before attempting to fix it. Here are some common file system issues you may encounter. File corruption. File corruption occurs when the data stored in a file becomes corrupted or unreadable. This can happen due to hardware failures, software bugs, or improper shutdowns. File corruption can lead to data loss or cause programs to crash or behave unexpectedly. Slow performance. If your file system is experiencing slow performance, it can significantly impact the overall system performance. Slow file operations, such as reading or writing files, can be caused by various factors, including disk fragmentation, insufficient disk space, or hardware issues. Unresponsive file operations. Sometimes, file operations may become unresponsive or hang indefinitely. This can occur due to issues with the file system driver, disk I/O errors, or resource contention. Unresponsive file operations can cause programs to freeze or become unresponsive. Debugging file system issues. When debugging file system issues, it is important to gather as much information as possible about the problem. This can help in identifying the root cause and finding an appropriate solution. Here are some techniques and tools you can use to debug file system issues in Linux. Checking file system integrity. The first step in debugging file system issues is to check the integrity of the file system. Linux provides several tools for this purpose, such as FSCK, File System Check, and E2FSCK, X2, X3, X4 File System Check. These tools scan the file system for errors and attempt to fix them. Running FSCK or E2FSCK with the appropriate options can help identify and repair file system inconsistencies. Monitoring file system activity. Monitoring file system activity can provide valuable insights into the behavior of the file system and help identify any abnormal patterns or bottlenecks. Tools like IOStat, VMSTAT, and ATOP can be used to monitor disk I/O, CPU usage, and other system metrics. By analyzing the output of these tools, you can identify any performance issues or resource constraints that may be affecting the file system. Analyzing system logs. System logs can contain valuable information about file system issues. The var log directory contains various log files that record system events, including file system errors and warnings. The dmesg command can be used to view the kernel ring buffer, which contains messages related to the file system and other kernel activities. Analyzing these logs can help pinpoint the cause of file system issues and guide the debugging process. Using file system-specific tools. Different file systems may have their own set of debugging tools and utilities. For example, the xfs_repair command is used to repair XFS file systems, while the btrfs_check command is used to check and repair btrfs file systems. Consult the documentation or online resources specific to your file system to learn about the available tools and their usage. Reproducing the issue. If possible, try to reproduce the file system issue in a controlled environment. This can help in isolating the problem and understanding its underlying causes. By reproducing the issue, you can gather additional information and test potential solutions without affecting the production system. Seeking help from the community. If you are unable to resolve the file system issue on your own, consider seeking help from the Linux community. Online forums, mailing lists, and IRC channels dedicated to Linux and file system debugging can provide valuable insights and guidance. Be sure to provide detailed information about the issue, including any error messages, system logs, and steps to reproduce the problem. Conclusion. Debugging file system issues in Linux can be a challenging task, but with the right techniques and tools, you can effectively identify and resolve these problems. By understanding the basics of file systems, common issues, and the debugging process, you will be better equipped to tackle file system issues in your Linux systems. Remember to gather as much information as possible, use appropriate tools, and seek help from the community when needed. 3.6 Debugging performance problems. Performance issues can significantly impact the overall functionality and user experience of a Linux system. These problems can manifest in various ways, such as slow response times, high CPU or memory usage, and excessive disk I/O. Debugging performance problems in Linux requires a systematic approach and the use of appropriate tools and techniques. In this section, we will explore some common performance issues and how to effectively debug them. Understanding performance problems. Before diving into the debugging process, it is essential to understand the nature of performance problems. Performance issues can arise from various sources, including inefficient algorithms, resource contention, hardware limitations, or misconfigurations. Identifying the root cause of a performance problem is crucial for effective debugging. Profiling tools. Profiling tools are essential for analyzing the performance of a Linux system. These tools provide insights into the resource utilization of processes and help identify bottlenecks. Some popular profiling tools in Linux include perf. Perf is a powerful performance analysis tool that comes pre-installed with many Linux distributions. It provides a wide range of features, including CPU profiling, event-based sampling, and hardware performance counters. Top. Top is a command line utility that provides real-time information about system processes and resource usage. It is useful for identifying processes that consume excessive CPU or memory. HTOP. HTOP is an interactive process viewer that provides a more user-friendly interface compared to top. It allows users to monitor system resources and manage processes efficiently. IOTOP. IOTOP is a tool for monitoring disk I/O usage in Linux. It displays a list of processes and their respective disk I/O usage, helping identify processes that are causing high disk activity. SAR. SAR, System Activity Reporter, is a command line utility that collects and reports system activity information. It can be used to monitor CPU, memory, disk, and network usage over time. Analyzing CPU usage. High CPU usage is a common performance problem in Linux systems. To identify processes that consume excessive CPU resources, tools like top or htop can be used. These tools display a list of processes sorted by CPU usage, allowing users to identify the culprits. Once the problematic processes are identified, further analysis can be done using the perf tool. Perf provides detailed information about CPU usage, including the number of instructions executed, cache misses, and branch miss predictions. This information can help pinpoint performance bottlenecks within the code. Monitoring memory usage. Excessive memory usage can lead to performance degradation and even system crashes. Tools like top or htop can be used to monitor memory usage and identify processes that consume a significant amount of memory. In addition to these tools, the vmstat command can provide valuable insights into memory usage. It displays information about virtual memory statistics, including the amount of free memory, swap usage, and page faults. By monitoring these statistics, users can identify memory-related performance issues. Analyzing disk I/O. Disk I/O can be a significant bottleneck in Linux systems, especially when dealing with large amounts of data. Tools like IOTop can help identify processes that are causing high disk activity. To gain a deeper understanding of disk I/O performance, the iostat command can be used. It provides detailed information about disk I/O statistics, including the number of read and write operations, the amount of data transferred, and the average response time. By analyzing these statistics, users can identify processes or devices that are causing excessive disk I/O. Network performance analysis. Network performance issues can impact the responsiveness and reliability of a Linux system. To analyze network performance, tools like netstat and tcpdump can be used. Netstat provides information about network connections, routing tables, and network interface statistics. It can help identify network-related performance issues, such as excessive connections or high packet loss. tcpdump is a packet analyzer that captures and analyzes network traffic. It can be used to monitor network packets and identify potential bottlenecks or anomalies. System-wide performance monitoring. To monitor system-wide performance, tools like SAR can be used. SAR collects and reports system activity information, including CPU, memory, disk, and network usage. By analyzing the collected data, users can identify performance trends and potential issues. Conclusion. Debugging performance problems in Linux requires a systematic approach and the use of appropriate tools. By understanding the nature of performance issues and utilizing profiling tools, users can effectively identify and resolve performance bottlenecks. Whether it's analyzing CPU usage, monitoring memory usage, analyzing disk I/O, or analyzing network performance, Linux provides a wide range of tools and techniques to debug and optimize system performance. 4. Advanced debugging techniques. 4.1 Debugging multi-threaded programs. Multi-threaded programming is a powerful technique used in Linux to improve the performance and responsiveness of applications. However, debugging multi-threaded programs can be challenging due to the inherent complexity of concurrent execution. In this section, we will explore various techniques and tools that can help you effectively debug multi-threaded programs in Linux. Understanding multi-threading issues. Multi-threaded programs introduce a new set of issues that can arise during execution. These issues include race conditions, deadlocks, and thread synchronization problems. Understanding these issues is crucial for effective debugging. A race condition occurs when two or more threads access shared resources simultaneously, leading to unpredictable behavior. Identifying race conditions can be difficult as they may only occur under specific timing conditions. Tools like Valgrind's Thread Sanitizer and Helgrind can help detect race conditions by analyzing memory access patterns and thread synchronization. Deadlocks occur when two or more threads are waiting for each other to release resources, resulting in a program freeze. Deadlocks can be challenging to debug as they often require careful analysis of thread interactions. Tools like GDB and SystemTap can be used to analyze thread states and identify potential deadlock scenarios. Thread synchronization problems can arise when threads are not properly coordinated, leading to incorrect results or program crashes. Techniques like mutexes, condition variables, and semaphores are commonly used to synchronize threads. However, incorrect usage of these synchronization primitives can introduce subtle bugs. Tools like GDB and Valgrind's Helgrind can help identify synchronization issues by analyzing thread interactions and memory access patterns. Debugging techniques for multi-threaded programs. When debugging multi-threaded programs, it is important to have a systematic approach to identify and resolve issues. Here are some techniques that can help you debug multi-threaded programs effectively. Reproduce the issue. Start by reproducing the issue in a controlled environment. This will help you isolate the problem and understand its root cause. Analyze thread interactions. Use tools like GDB to analyze the interactions between threads. Set breakpoints at critical sections of code and observe the behavior of each thread. Use GDB commands like info threads to get information about the current state of each thread. Use thread-safe debugging techniques. When debugging multi-threaded programs, it is important to use thread-safe debugging techniques. Avoid using global variables or shared resources that can introduce race conditions. Instead, use thread local variables or thread-safe data structures. Enable debugging symbols. Ensure that your program is compiled with debugging symbols enabled. This will provide more meaningful information when analyzing thread states and stack traces. Use logging and debugging statements. Insert logging statements in critical sections of code to track the execution flow of each thread. Use debugging statements to print relevant information about thread states, variable values, and synchronization primitives. Analyze core dumps. If your program crashes, analyze the core dump to understand the state of the program at the time of the crash. Tools like GDB can help you analyze core dumps and identify the cause of the crash. Use thread-safe libraries. When using external libraries in your multi-threaded program, ensure that they are thread-safe. Using non-thread-safe libraries can introduce subtle bugs and make debugging more challenging. Use debugging tools. Linux provides several debugging tools that can help you analyze multi-threaded programs. Tools like GDB, Valgrind, and SystemTap offer features specifically designed for debugging multi-threaded programs. Debugging tools for multi-threaded programs. Linux provides a range of powerful tools that can assist in debugging multi-threaded programs. Here are some commonly used tools. GDB. The new debugger GDB is a powerful command line tool for debugging programs. It allows you to set breakpoints, examine thread states, and analyze stack traces. GDB also provides features for analyzing core dumps and attaching to running processes. Valgrind. Valgrind is a suite of tools that can help you detect memory leaks, race conditions, and other memory-related issues. Tools like memcheck and thread sanitizer can be used to analyze multi-threaded programs and identify memory-related bugs. SystemTap. SystemTap is a dynamic tracing tool that allows you to trace and analyze the behavior of the Linux kernel and user space programs. It provides a scripting language that can be used to write custom probes and analyze multi-threaded programs. Helgrind. Helgrind is a tool provided by Valgrind that specifically targets multi-threaded programs. It can detect race conditions, deadlocks, and other synchronization issues by analyzing thread interactions and memory access patterns. pthread library. The pthread library provides a set of functions and data structures for creating and managing threads in Linux. It also provides debugging features like thread-specific data and thread attribute objects that can be used to debug multi-threaded programs. By using these tools and techniques, you can effectively debug multi-threaded programs in Linux and resolve issues related to race conditions, deadlocks, and thread synchronization problems. Remember to have a systematic approach and use the appropriate tools for each debugging scenario. 4.2 Debugging deadlocks and race conditions. Deadlocks and race conditions are common issues that can occur in multi-threaded programs. These issues can be difficult to debug and can lead to unexpected behavior and program crashes. In this section, we will explore techniques for debugging deadlocks and race conditions in Linux. Understanding deadlocks. A deadlock occurs when two or more threads are waiting for each other to release resources, resulting in a situation where none of the threads can proceed. Deadlocks can be caused by various factors, such as improper resource allocation, incorrect locking order, or missing lock release. To debug deadlocks, it is important to first identify the threads involved in the deadlock. This can be done by analyzing the program's stack traces or using debugging tools such as GDB. Once the threads involved in the deadlock are identified, it is necessary to analyze the code to determine the cause of the deadlock. Analyzing deadlocks. One approach to analyzing deadlocks is to use a tool called Valgrind. Valgrind is a powerful debugging and profiling tool that can detect various types of errors, including deadlocks. By running the program under Valgrind, it can detect potential deadlocks and provide detailed information about the threads involved and the resources they are waiting for. Another useful tool for analyzing deadlocks is Helgrind, which is a part of the Valgrind suite. Helgrind specifically focuses on detecting and analyzing thread synchronization issues, including deadlocks and race conditions. By running the program under Helgrind, it can detect potential deadlocks and provide detailed information about the synchronization primitives used by the threads. Debugging race conditions. Race conditions occur when multiple threads access shared resources concurrently, leading to unpredictable behavior. Race conditions can be challenging to debug because they often depend on the timing and scheduling of the threads. To debug race conditions, it is important to first identify the shared resources that are being accessed by multiple threads. This can be done by analyzing the code and identifying variables or data structures that are accessed by multiple threads without proper synchronization. Once the shared resources are identified, it is necessary to analyze the code to determine the cause of the race condition. This may involve inspecting the code for missing or incorrect synchronization primitives, such as locks or atomic operations. Analyzing race conditions. There are several tools available for analyzing race conditions in Linux programs. One such tool is Thread Sanitizer (TSAN), which is a part of the LLVM compiler infrastructure. TSAN can detect and report race conditions by instrumenting the program's code and monitoring memory accesses and synchronization operations. Another useful tool for analyzing race conditions is Helgrind, which we mentioned earlier. In addition to detecting deadlocks, Helgrind can also detect and analyze race conditions. By running the program under Helgrand, it can detect potential race conditions and provide detailed information about the threads involved and the shared resources they are accessing. Debugging techniques for deadlocks and race conditions. When debugging deadlocks and race conditions, it is important to have a systematic approach. Here are some techniques that can be helpful. Reproduce the issue. Try to reproduce the deadlock or race condition consistently. This will make it easier to analyze and debug the issue. Use logging and debugging statements. Insert logging statements in the code to track the execution flow and identify the points where threads are waiting or accessing shared resources. Use debugging tools like GDB to step through the code and inspect variables and data structures. Analyze thread interactions. Analyze the interactions between threads to identify potential synchronization issues. Look for cases where threads are waiting for each other or accessing shared resources without proper synchronization. Use synchronization primitives correctly. Ensure that synchronization primitives like locks, mutexes, and condition variables are used correctly and consistently. Make sure that locks are acquired and released in the correct order to avoid deadlocks. Use thread-safe data structures. Use thread-safe data structures and libraries whenever possible to minimize the chances of race conditions. Avoid sharing mutable data across threads unless necessary. Stress testing. Perform stress testing by running the program with a large number of threads or inputs to expose potential race conditions or deadlocks. This can help uncover issues that may not be apparent during normal execution. By following these techniques and using the appropriate debugging tools, you can effectively debug deadlocks and race conditions in Linux programs. Remember that debugging these issues can be challenging, so patience and persistence are key. 4.3 Debugging memory leaks. Memory leaks are a common issue in software development, and debugging them can be a challenging task. In this section, we will explore techniques and tools for debugging memory leaks in Linux. Understanding memory leaks. Before diving into the debugging process, it is essential to understand what memory leaks are and how they occur. A memory leak happens when a program fails to release memory that it no longer needs, resulting in a gradual accumulation of memory usage over time. This can lead to performance degradation, crashes, and even system instability. Memory leaks can occur due to various reasons, such as unreleased memory allocation. When a program dynamically allocates memory using functions like malloc or new, it must release that memory using free or delete when it is no longer needed. Forgetting to release memory can result in a memory leak. Cyclic references. In languages like C++ or Java, objects can reference each other in a circular manner. If these references are not properly managed, it can prevent the garbage collector from reclaiming memory, leading to memory leaks. Unclosed resources. In addition to memory, other system resources like file handles or network connections can also leak if they are not properly closed or released. Detecting memory leaks. Detecting memory leaks can be a complex task, especially in large codebases. However, there are several techniques and tools available to help identify and debug memory leaks in Linux. Manual inspection. One approach to detecting memory leaks is through manual inspection of the code. By carefully reviewing the codebase, developers can identify potential areas where memory leaks may occur. This involves looking for instances where memory is allocated but not released, or where resources are not properly closed. While manual inspection can be effective for small codebases, it becomes increasingly challenging as the code size grows. Additionally, it may not catch subtle memory leaks that occur in specific scenarios or edge cases. Memory profilers. Memory profilers are specialized tools designed to track memory allocations and deallocations in a program. These tools provide detailed information about memory usage, including the allocation size, location, and call stack. Valgrind is a popular memory profiling tool in the Linux ecosystem. It provides a suite of tools, including memcheck, which can detect memory leaks, invalid memory accesses, and other memory-related errors. By running the program under Valgrind's supervision, developers can identify memory leaks and pinpoint the exact location in the code where the leak occurs. Another widely used memory profiler is Address Sanitizer, ASAN, which is part of the LLVM compiler infrastructure. ASAN instruments the program's memory operations and detects memory errors, including memory leaks. It provides detailed reports that help identify the source of the leaks. Garbage collection. Languages like Java and C# have built-in garbage collectors that automatically manage memory allocation and deallocation. These garbage collectors can detect and reclaim memory that is no longer in use, including memory leaks caused by cyclic references. If you are working with a language that has a garbage collector, it is essential to understand its behavior and configuration options. Tuning the garbage collector settings can help mitigate memory leaks and improve overall memory management. Debugging tools. In addition to memory profilers, there are several debugging tools available in Linux that can assist in detecting memory leaks. These tools provide insights into memory usage and can help identify potential leaks. One such tool is the GNU Debugger (GDB), which is a powerful command line debugger. GDB allows developers to inspect the program's memory, set breakpoints, and analyze the call stack. By using GDB, developers can track memory allocations and deallocations, helping to identify memory leaks. Another useful tool is the electric fence library, which can be used to detect buffer overflows and memory access errors. When a program uses electric fence, it replaces the standard memory allocation functions with its own versions that detect illegal memory accesses. This can help identify memory leaks caused by incorrect memory access. Debugging memory leaks. Once a memory leak is detected, the next step is to debug and fix it. Here are some general steps to follow when debugging memory leaks. Reproduce the issue. Start by identifying a specific scenario or input that triggers the memory leak. This will help narrow down the problem and make it easier to debug. Use memory profiling tools. Run the program under a memory profiler like Valgrind or Asan to identify the source of the memory leak. These tools will provide detailed information about the memory allocations and deallocations, helping to pinpoint the exact location of the leak. Analyze the call stack. Once the memory leak is identified, analyze the call stack to understand the sequence of function calls that lead to the leak. This will help identify any missing deallocations or incorrect memory management. Fix the memory leak. Once the root cause of the memory leak is identified, fix the issue by properly releasing the allocated memory or closing any unclosed resources. Make sure to test the fix thoroughly to ensure that it resolves the memory leak without introducing any new issues. Monitor and verify. After fixing the memory leak, monitor the program's memory usage to ensure that the leak has been resolved. Use memory profiling tools or system monitoring utilities to verify that the memory usage remains stable over time. Debugging memory leaks can be a time-consuming process, but with the right tools and techniques, it is possible to identify and fix these issues effectively. By understanding the causes of memory leaks and using appropriate debugging tools, developers can ensure that their Linux applications are free from memory leaks and perform optimally. 4.4 Debugging segmentation faults. Segmentation faults, also known as segfaults, are a common type of error that occurs when a program tries to access a memory location that it is not allowed to access. This can happen due to various reasons, such as accessing a null pointer, accessing an array out of bounds, or trying to execute data as code. Segmentation faults can be particularly challenging to debug because they often result in the program crashing or terminating abruptly. When a segmentation fault occurs, the operating system sends a signal to the program, indicating that it has accessed an invalid memory location. By default, the program terminates and produces a core dump file, which contains a snapshot of the program's memory at the time of the crash. This core dump file can be analyzed to understand the cause of the segmentation fault. To debug segmentation faults in Linux, you can use various tools and techniques. Here are some approaches that can help you identify and fix these issues. 1. Analyzing the core dump. When a program crashes due to a segmentation fault, it generates a core dump file. This file contains valuable information about the state of the program at the time of the crash, including the memory layout, register values, and the call stack. You can use the GDB debugger to analyze the core dump and identify the cause of the segmentation fault. To analyze a core dump with GDB, use the following command. GDB less than executable greater than less than core underscore dump underscore file greater than. Once you are in the GDB prompt, you can use various commands to examine the program's state. For example, you can use the bt command to display the backtrace, which shows the sequence of function calls that led to the segmentation fault. You can also inspect the values of variables and registers to understand the state of the program. 2. Using Address Sanitizer. Address Sanitizer (ASAN) is a powerful tool for detecting memory errors, including segmentation faults. It is available in modern versions of the GNU Compiler Collection (GCC) and Clang. ASAN instruments the program's memory operations to detect invalid memory accesses at runtime. To enable ASAN, compile your program with the fsanitize equals address flag. For example, gcc fsanitize equals address o my underscore program, c. When the program is executed, ASAN will detect any memory errors, including segmentation faults, and provide detailed information about the error, such as the exact location where the invalid memory access occurred. 3. Using Valgrind. Valgrind is a powerful debugging and profiling tool that can help you detect and diagnose a wide range of memory-related errors, including segmentation faults. It provides a suite of tools, including memcheck, which can detect memory leaks, buffer overflows, and other memory errors. To use Valgrind to debug a program, run it with the Valgrind command followed by the name of the executable. For example, Valgrind, my underscore program. Valgrind will analyze the program's memory usage and report any memory errors it detects, including segmentation faults. It will provide detailed information about the error, such as the exact location in the code where the invalid memory access occurred. 4. Reviewing the code. Sometimes, the cause of a segmentation fault can be identified by carefully reviewing the code. Look for common programming mistakes, such as accessing arrays out of bounds, dereferencing null pointers, or using uninitialized variables. Use code review tools and static analyzers to catch potential issues before they cause segmentation faults. 5. Debugging with print statements. One of the simplest and most effective ways to debug segmentation faults is by using print statements in your code. By strategically placing print statements before and after critical sections of code, you can narrow down the location where the segmentation fault occurs. Print the values of variables and pointers to identify any inconsistencies or unexpected behavior. 6. Narrowing down the problem. If you are dealing with a large codebase, it can be challenging to identify the exact cause of a segmentation fault. In such cases, it is helpful to narrow down the problem by isolating the code that triggers the segmentation fault. You can do this by systematically commenting out sections of code until the segmentation fault no longer occurs. This process of elimination can help you identify the specific code or function that is causing the issue. 7. Using debugging tools. In addition to GDB, Valgrind, and Asan, there are several other debugging tools available in Linux that can help you debug segmentation faults. These include strace, which traces system calls and signals, and ltrace, which traces library calls. These tools can provide valuable insights into the program's behavior and help identify the cause of the segmentation fault. Debugging segmentation faults can be a challenging task, but with the right tools and techniques, you can effectively identify and fix these issues. By analyzing core dumps, using tools like Asan and Valgrind, reviewing the code, and narrowing down the problem, you can gain a deeper understanding of the root cause of the segmentation fault and take appropriate steps to resolve it. 5. Debugging with GDB. 5.1 Introduction to GDB. GDB, which stands for New Debugger, is a powerful and widely used debugging tool in the Linux environment. It is a command line tool that allows developers to analyze and debug programs written in various programming languages, including C, C++, Python, and more. GDB provides a range of features and capabilities that aid in identifying and resolving software bugs, making it an essential tool for Linux developers. Why use GDB? Debugging is an essential part of the software development process. It involves identifying and fixing errors, known as bugs, in a program. GDB simplifies this process by providing developers with a set of tools and features that enable them to analyze the program's execution, inspect variables, and track down the root cause of the bug. Here are some reasons why GDB is widely used for debugging in Linux. Interactive debugging. GDB allows developers to interactively debug their programs. They can set breakpoints at specific lines of code, step through the program's execution, and examine the values of variables at different points in the program. This interactive approach helps developers gain a deeper understanding of the program's behavior and identify the source of the bug more effectively. Multi-language support. GDB supports a wide range of programming languages, making it a versatile tool for developers working on different projects. Whether you are debugging a C program, a Python script, or a C++ application, GDB provides the necessary tools and features to analyze and debug the code. Core dump analysis. GDB can analyze core dump files generated when a program crashes. Core dumps contain a snapshot of the program's memory at the time of the crash, allowing developers to examine the state of the program and identify the cause of the crash. GDB can load core dump files and provide a detailed analysis of the program's state, helping developers understand what went wrong. Post-mortem debugging. GDB can also be used for post-mortem debugging, which involves analyzing a program's behavior after it has crashed or terminated unexpectedly. By examining the program's core dump or log files, developers can use GDB to understand the sequence of events leading up to the crash and identify the root cause of the issue. Scripting support. GDB provides a scripting interface that allows developers to automate repetitive debugging tasks. By writing scripts in languages like Python or TCL, developers can extend GDB's functionality and create custom debugging workflows tailored to their specific needs. Getting started with GDB. To start using GDB, you need to have it installed on your Linux system. Most Linux distributions include GDB in their package repositories, so you can install it using the package manager specific to your distribution. For example, on Ubuntu, you can install GDB by running the following command: sudo apt-get install GDB. Once GDB is installed, you can start using it by running the GDB command followed by the name of the program you want to debug. For example, to debug a C program called myprogram, you would run GDB myprogram. This will start GDB and load the specified program. From here, you can use various GDB commands to analyze and debug the program. Basic GDB commands. GDB provides a set of basic commands that are commonly used during the debugging process. Here are some of the essential commands. Break sets a breakpoint at a specific line of code or function. Run starts the execution of the program. Next executes the next line of code. Step steps into a function call. Continue continues the execution until the next breakpoint or program termination. Print prints the value of a variable. Backtrace displays the current call stack. Quit exits GDB. These commands provide a starting point for debugging your programs with GDB. As you become more familiar with GDB, you can explore its advanced features and techniques to enhance your debugging workflow. Conclusion. GDB is a powerful and versatile debugging tool that plays a crucial role in the Linux development ecosystem. Its interactive debugging capabilities, multi-language support, and core dump analysis features make it an invaluable tool for developers. By mastering GDB, you can effectively identify and fix bugs in your Linux programs, improving the overall quality and reliability of your software. 5.2 Basic GDB Commands. GDB, new debugger, is a powerful command line tool used for debugging programs in Linux. It provides a wide range of features and commands to help developers analyze and fix issues in their code. In this section, we will explore some of the basic GDB commands that are essential for debugging Linux programs effectively. Starting a program in GDB. To start debugging a program using GDB, you need to launch GDB and specify the program you want to debug as an argument. For example, to debug a program called my program, you would run the following command: GDB my program. Once GDB starts, it will display a prompt where you can enter commands to interact with the debugger. Setting breakpoints. Breakpoints are one of the most commonly used features in GDB. They allow you to pause the execution of a program at a specific line of code or function. This allows you to inspect the program's state and variables at that point. To set a breakpoint at a specific line of code, use the break command followed by the line number. For example, to set a breakpoint at line 10, you would run break 10. You can also set breakpoints at specific functions by specifying the function name instead of the line number. For example, break my function. To view all the breakpoints that have been set, you can use the info breakpoints command. Running the program. Once you have set your breakpoints, you can start running the program using the run command. This will execute the program until it reaches the first breakpoint or until it completes its execution. Run. If the program encounters a breakpoint, it will pause and return control to the GDB prompt. Examining variables. GDB allows you to examine the values of variables at any point during program execution. The print command is used to display the value of a specific variable. For example, to print the value of a variable called myvar, you would run print myvar. You can also use the display command to continuously display the value of a variable as the program executes. This can be useful when you want to monitor the value of a variable over time. Stepping through the code. GDB provides several commands to step through the code and control the program's execution. The most commonly used commands are: next, executes the next line of code and stops at the following line. Step, executes the next line of code and stops at the first line of any called function. Finish, executes the remaining lines of the current function and stops at the line that called the function. These commands allow you to navigate through the program's execution and observe how the variables and program state change. Examining the call stack. The call stack is a crucial tool for understanding the flow of program execution and tracking function calls. GDB provides the backtrace command to display the current call stack. This command shows the sequence of function calls that led to the current point in the program. Backtrace. Each entry in the call stack represents a function call, with the most recent call at the top. The call stack provides valuable information about the program's execution flow and can help identify where an issue occurred. Modifying program execution. GDB allows you to modify the execution of a program by changing the values of variables or altering the program's flow. The set command is used to modify the value of a variable. For example, to change the value of a variable called myvar to 10, you would run set myvar equals 10. You can also use the jump command to jump to a specific line of code or function. This can be useful when you want to skip certain parts of the program or repeat a specific section. Exiting GDB. To exit GDB, you can use the quit command or simply press Ctrl+D on your keyboard. Before exiting, GDB will prompt you to confirm if you want to quit. These are just some of the basic GDB commands that can help you get started with debugging Linux programs. GDB provides many more commands and features that can assist you in analyzing and fixing issues in your code. It is recommended to explore the GDB documentation and experiment with different commands to become proficient in using this powerful debugging tool. 5.3 Advanced GDB Features. In the previous sections, we have covered the basics of using GDB to debug programs in Linux. GDB is a powerful tool that provides a wide range of features to help you analyze and troubleshoot your code. In this section, we will explore some of the advanced features of GDB that can further enhance your debugging experience. 5.3.1 Conditional breakpoints. One of the most useful features of GDB is the ability to set conditional breakpoints. A breakpoint is a point in your code where the debugger will pause execution and allow you to inspect the program's state. With conditional breakpoints, you can specify a condition that must be met for the breakpoint to be triggered. To set a conditional breakpoint, you can use the break command followed by the line number or function name where you want to set the breakpoint. For example, to set a breakpoint at line 10 of a C program, you can use the following command: break 10 if x equals 0. This will set a breakpoint at line 10, but only if the variable x is equal to 0. When the breakpoint is hit, you can use the print command to inspect the value of x and other variables in the program. Conditional breakpoints can be extremely helpful when you want to debug a specific scenario or when you want to avoid stopping the program at every iteration of a loop. By setting a condition, you can ensure that the breakpoint is triggered only when certain conditions are met. 5.3.2 Watchpoints. Another powerful feature of GDB is watchpoints. Watchpoints allow you to monitor the value of a variable and break execution when the value changes. This can be particularly useful when you suspect that a certain variable is being modified incorrectly or when you want to track the changes in a specific variable during program execution. To set a watch point, you can use the watch command followed by the variable name. For example, to watch the variable count in a C program, you can use the following command. Watch count. When the value of count changes, GDB will break execution and allow you to inspect the program's state. You can then use the print command to view the new value of count and analyze the changes. Watch points can be set on both global and local variables, and they can also be set on memory locations. This allows you to track changes in variables and memory regions that are critical to your program's execution. 5.3.3 Reverse Debugging. GDB also supports reverse debugging, which allows you to step backward through your program's execution. This can be particularly useful when you want to understand how a certain bug or error occurred by going back in time and inspecting the program's state at different points. To enable reverse debugging, you can use the reverse step command to step backward one instruction at a time. You can also use the reverse continue command to continue execution in reverse until the next breakpoint or until the program reaches the beginning. Reverse debugging can be a powerful tool for understanding the sequence of events that led to a bug or error. By stepping backward and inspecting the program's state at different points, you can gain valuable insights into the root cause of the issue. 5.3.4 Post-mortem debugging. GDB also supports post-mortem debugging, which allows you to analyze a core dump file generated by a crashed program. A core dump file contains a snapshot of the program's memory at the time of the crash, which can be invaluable for understanding the cause of the crash. To debug a core dump file, you can use the core command followed by the path to the core dump file. This will load the core dump file into GDB and allow you to inspect the program's state at the time of the crash. Once the core dump file is loaded, you can use the same GDB commands as you would for live debugging, such as setting breakpoints, inspecting variables, and stepping through the code. This can help you analyze the state of the program at the time of the crash and identify the root cause of the issue. Post-mortem debugging can be a valuable technique for troubleshooting crashes and errors that occur in production environments. By analyzing core dump files, you can gain insights into the cause of the crash and make the necessary fixes to prevent similar issues in the future. 5.3.5 Dynamic loading and unloading of shared libraries. GDB also provides support for dynamically loading and unloading shared libraries during program execution. This can be useful when you want to debug a program that uses dynamically loaded libraries or when you want to analyze the behavior of a specific library. To load a shared library, you can use the shared library command followed by the path to the library file. This will load the library into the program's address space and allow you to set breakpoints and analyze its behavior. Similarly, to unload a shared library, you can use the unload command followed by the library name or address. This will remove the library from the program's address space and prevent further execution within the library. Dynamic loading and unloading of shared libraries can be helpful when you want to focus your debugging efforts on a specific library or when you want to analyze the interactions between different libraries in your program. Conclusion. In this section, we have explored some of the advanced features of GDB that can enhance your debugging experience. Conditional breakpoints, watch points, reverse debugging, post-mortem debugging, and dynamic loading and unloading of shared libraries are powerful tools that can help you analyze and troubleshoot your code more effectively. By mastering these advanced features, you can become a more proficient Linux debugger and tackle even the most complex debugging challenges. 5.4 Remote debugging with GDB. Remote debugging is a powerful technique that allows developers to debug programs running on a remote machine. This is particularly useful when the development environment and the target machine are physically separated, such as in the case of embedded systems or distributed systems. In this section, we will explore how to perform remote debugging using GDB, the new debugger. Setting up the remote debugging environment. To perform remote debugging with GDB, you need to have GDB installed on both the local and remote machines. Additionally, you need to ensure that the remote machine has debugging symbols available for the program you want to debug. Debugging symbols contain information about the source code, variables, and functions, which is essential for meaningful debugging. To generate debugging symbols during the compilation process, you can use the G flag with the compiler. For example, to compile a C program with debugging symbols, you can use the following command. gccg program, co program. Once you have the necessary setup on the remote machine, you can proceed with remote debugging. Connecting to the remote machine. To connect to the remote machine for debugging, you need to use the target remote command in GDB. This command establishes a connection between the local GDB instance and the remote GDB server running on the remote machine. The syntax for connecting to the remote machine is as follows. Target remote less than remote machine greater than, less than port greater than. Here, less than remote machine greater than is the IP address or hostname of the remote machine, and less than port greater than is the port number on which the GDB server is running. The GDB server is responsible for handling the debugging requests from the local GDB instance. Before connecting to the remote machine, ensure that the GDB server is running on the remote machine. You can start the GDB server by executing the following command on the remote machine. GDB server less than port greater than less than executable greater than. Here, less than port greater than is the port number on which the GDB server should listen for connections, and less than executable greater than is the path to the executable file on the remote machine. Once the GDB server is running on the remote machine, you can connect to it from the local machine using the target remote command. For example, to connect to a remote machine with IP address 192.168.1.100 running the GDB server on port 1234, you can use the following command in GDB. Target remote 192.168.1.100, 1234 remote debugging commands. Once the connection is established, you can use the same set of GDB commands for remote debugging as you would for local debugging. You can set breakpoints, step through the code, examine variables, and perform other debugging operations. Some commonly used remote debugging commands in GDB include break or B, set a breakpoint at a specific line or function. Continue or C, continue execution until the next breakpoint or program termination. Next or N, execute the next line of code. Step or S, step into a function call. Print or P, print the value of a variable. Backtrace or BT, print the current call stack. Quit or Q, quit the GDB session. Limitations of remote debugging. While remote debugging with GDB is a powerful technique, it does have some limitations. The most significant limitation is the potential for increased latency and reduced responsiveness due to the network connection between the local and remote machines. This can make the debugging process slower and less interactive compared to local debugging. Additionally, remote debugging may not be suitable for certain scenarios, such as debugging real-time systems or debugging programs that rely heavily on hardware interactions. In these cases, it is often more effective to use other debugging techniques specific to the target environment. Conclusion. Remote debugging with GDB is a valuable technique for debugging programs running on remote machines. By establishing a connection between the local GDB instance and the remote GDB server, developers can effectively debug programs in environments where the development and target machines are physically separated. However, it is important to be aware of the limitations of remote debugging and consider alternative debugging techniques when necessary. 6. Debugging with SystemTap. 6.1 Introduction to SystemTap. SystemTap is a powerful and flexible tracing and probing tool for Linux systems. It allows developers and system administrators to monitor and analyze the behavior of the Linux kernel and user space applications in real time. With SystemTap, you can gather detailed information about system activities, performance bottlenecks, and potential issues, making it an invaluable tool for debugging and performance tuning. What is SystemTap? SystemTap is a scripting language and runtime infrastructure that provides a high-level interface for dynamic tracing and probing of the Linux kernel and user space applications. It allows you to write custom scripts that can be dynamically loaded into the running kernel or attached to specific processes to collect data and perform analysis. Unlike traditional debugging tools like GDB, which require recompiling the code with debug symbols, SystemTap operates at the system level and does not require any modifications to the target application or kernel. This makes it particularly useful for debugging production systems or closed-source applications where source code access may not be available. Key features of SystemTap. SystemTap offers several key features that make it a powerful tool for debugging and performance analysis. Dynamic tracing. SystemTap allows you to dynamically instrument the Linux kernel and user space applications without the need for recompilation. You can write scripts that specify the events or functions you want to trace and collect data in real time. Flexible scripting language. SystemTap uses a scripting language based on the C programming language, making it easy to write and understand scripts. It provides a rich set of built-in functions and libraries for performing complex analysis and data manipulation. Probing and monitoring. SystemTap allows you to probe and monitor various system activities, such as function calls, system calls, kernel events, and hardware events. You can collect data at different levels of granularity, from individual function calls to system-wide activities. Customizable output. SystemTap provides flexible output options, allowing you to format and display the collected data in various ways. You can generate textual reports, histograms, graphs, or even integrate with external tools for further analysis. Safety and security. SystemTap is designed to be safe and secure. It operates within the confines of the Linux kernel's security model and enforces strict access controls. Scripts are executed in a controlled environment, preventing them from causing harm to the system. Use cases for SystemTap. SystemTap can be used in a wide range of scenarios for debugging and performance analysis. Some common use cases include kernel debugging. SystemTap allows you to trace and analyze the behavior of the Linux kernel, making it useful for diagnosing kernel-level issues such as crashes, hangs, or performance bottlenecks. Application debugging. SystemTap can be used to trace and monitor the execution of user space applications. It enables you to gather detailed information about function calls, system calls, and other events, helping you identify and fix bugs or performance problems. Performance tuning. SystemTap provides insights into system performance by allowing you to monitor various metrics, such as CPU usage, memory usage, disk I/O, and network activity. You can use this information to identify performance bottlenecks and optimize system resources. Security analysis. SystemTap can be used to monitor system activities and detect potential security vulnerabilities or suspicious behavior. By tracing system calls, network traffic, or file accesses, you can identify and investigate security incidents. Getting started with SystemTap. To start using SystemTap, you need to install the SystemTap package on your Linux system. The package includes the SystemTap runtime, scripting language, and development tools. Once installed, you can write SystemTap scripts using a text editor and execute them using the stab command. SystemTap provides a rich set of documentation and examples to help you get started. The official SystemTap website offers tutorials, user guides, and a comprehensive reference manual. Additionally, there are numerous online resources, forums, and communities where you can find support and share your experiences with SystemTap. In the next section, we will explore the process of writing SystemTap scripts and demonstrate how to use SystemTap to analyze system performance. Summary. SystemTap is a powerful tracing and probing tool for Linux systems that allows you to monitor and analyze the behavior of the Linux kernel and user space applications. It offers dynamic tracing, flexible scripting, and customizable output options, making it a valuable tool for debugging and performance analysis. SystemTap can be used in various scenarios, including kernel debugging, application debugging, performance tuning, and security analysis. To get started with SystemTap, you need to install the SystemTap package and refer to the available documentation and examples. 6.2 Writing SystemTap scripts. SystemTap is a powerful tool for debugging and tracing Linux systems. It allows you to write scripts that can dynamically instrument the kernel and user space programs to gather information about their behavior. In this section, we will explore the basics of writing SystemTap scripts and how they can be used for debugging purposes. Understanding SystemTap. SystemTap is a scripting language that provides a high-level interface for tracing and monitoring the Linux kernel and user space programs. It allows you to write scripts that can be dynamically loaded into the kernel and execute in real time. These scripts can be used to gather information about system events, function calls, and variable values, which can be invaluable for debugging purposes. SystemTap scripts are written in AC-like syntax and consist of a series of probes. Probes are points in the code where the script can be executed. They can be placed at various locations, such as function entry and exit points, system call entry and exit points, and timer events. When a probe is hit, the script is executed, and you can collect data, print messages, or perform other actions. Writing SystemTap scripts. To write a SystemTap script, you need to have the SystemTap tool installed on your Linux system. Once installed, you can create a new script file with a.stp extension and start writing your script. A basic SystemTap script consists of three main parts: the probe, the handler, and the output. The probe defines the point in the code where the script should be executed. The handler contains the code that will be executed when the probe is hit. And the output specifies how the collected data should be displayed. Here's an example of a simple SystemTap script that traces the execution of a specific function. Probe process path to executable, function _name. Printf function %s called n, probe func. In this script, the probe statement specifies that the script should be executed whenever the function named, function _name, is called in the executable located at path to executable. The handler contains a printf statement that prints a message indicating that the function has been called. The probe func function is a built-in SystemTap function that returns the name of the function being probed. You can run the SystemTap script using the stab command followed by the script file name. The output will be displayed in the terminal. Advanced SystemTap features. SystemTap provides a wide range of features that allow you to gather detailed information about the system's behavior. Here are some advanced features that you can use in your SystemTap scripts. Variables. You can define and use variables in your SystemTap scripts to store and manipulate data. SystemTap supports various data types, including integers, strings, arrays, and structures. Conditionals and loops. SystemTap allows you to use conditionals and loops in your scripts to control the flow of execution. You can use if-else statements, switch statements, and for and while loops to perform different actions based on certain conditions. Function calls. SystemTap provides built-in functions that allow you to call external functions from your scripts. This can be useful when you need to perform complex calculations or interact with the system in a specific way. Aggregations. SystemTap allows you to aggregate data over time using functions such as sum, avg, and count. This can be useful when you want to track the occurrence of certain events or calculate statistics. User space tracing. In addition to tracing the kernel, SystemTap can also trace user space programs. You can use the probe statement with the process function to specify the executable and function you want to trace. Debugging with SystemTap. SystemTap can be a powerful tool for debugging Linux systems. By writing custom SystemTap scripts, you can gather detailed information about the system's behavior and identify potential issues. Here are some ways you can use SystemTap for debugging. Tracing function calls. You can use SystemTap to trace the execution of specific functions in your code. By printing messages or collecting data at function entry and exit points, you can gain insights into the flow of your program and identify any unexpected behavior. Monitoring system calls. SystemTap allows you to trace system calls made by your program. This can be useful for identifying issues related to file I/O, network communication, or process management. Tracking variable values. SystemTap allows you to monitor the values of variables in real time. By printing the values of critical variables at specific points in your code, you can identify any unexpected changes or inconsistencies. Analyzing performance. SystemTap can be used to analyze the performance of your system or specific parts of your code. By measuring the execution time of functions or tracking resource usage, you can identify performance bottlenecks and optimize your code. Debugging kernel modules. SystemTap can also be used to debug kernel modules. By writing SystemTap scripts that trace the execution of specific kernel functions or monitor the values of kernel variables, you can gain insights into the behavior of your module and identify any issues. Conclusion. SystemTap is a powerful tool for debugging and tracing Linux systems. By writing custom SystemTap scripts, you can gather detailed information about the system's behavior and identify potential issues. In this section, we explored the basics of writing SystemTap scripts and how they can be used for debugging purposes. We also discussed some advanced features of SystemTap and how it can be used to debug kernel modules. With SystemTap, you have a powerful tool at your disposal to help you debug and optimize your Linux systems. 6.3 Analyzing system performance with SystemTap. System performance is a critical aspect of any Linux system, and being able to analyze and optimize it is essential for maintaining a high-performing environment. SystemTap is a powerful tool that allows you to monitor and analyze system performance in real time. In this section, we will explore how to use SystemTap to analyze system performance and identify performance bottlenecks. Understanding system performance analysis. System performance analysis involves monitoring various system metrics and identifying areas where the system is underperforming or experiencing bottlenecks. By analyzing system performance, you can identify resource-intensive processes, memory leaks, disk I/O issues, and other performance-related problems. SystemTap provides a scripting language and a set of tools that allow you to write custom scripts to monitor and analyze system performance. These scripts can be used to collect data on various system activities, such as CPU usage, memory usage, disk I/O, network activity, and more. By analyzing this data, you can gain insights into the system's behavior and identify areas for improvement. Writing SystemTap performance scripts. To analyze system performance with SystemTap, you need to write custom scripts that define the metrics you want to monitor and the actions to be taken when certain conditions are met. SystemTap scripts are written in AC-like language and can be compiled and executed on the target system. Here are some key steps to follow when writing SystemTap performance scripts. Define the probe points. Probe points are specific locations in the system where you want to collect data. These can be function entry, exit points, system calls, kernel events, or any other point of interest. SystemTap provides a wide range of predefined probe points that you can use in your scripts. Specify the data to collect. Once you have defined the probe points, you need to specify the data you want to collect at those points. This can include CPU usage, memory usage, disk I/O statistics, network activity, and more. SystemTap provides a set of built-in functions and variables that allow you to access and collect this data. Define the conditions. Next, you need to define the conditions under which you want to collect the data. For example, you may want to collect CPU usage data only when it exceeds a certain threshold or collect disk I/O statistics only for a specific process. SystemTap provides a rich set of operators and control structures that allow you to define complex conditions. Take actions. Finally, you need to specify the actions to be taken when the specified conditions are met. This can include printing the collected data, generating log files, sending notifications, or executing custom commands. SystemTap provides a range of built-in functions and macros that allow you to perform these actions. Analyzing system performance data. Once you have written and executed your SystemTap performance scripts, you will start collecting data on various system activities. Analyzing this data is crucial for identifying performance bottlenecks and optimizing system performance. Here are some techniques you can use to analyze system performance data. Data visualization. SystemTap provides built-in functions for printing collected data in a human-readable format. You can use these functions to print data to the console or generate log files. By visualizing the data, you can quickly identify patterns, trends, and anomalies. Statistical analysis. SystemTap allows you to perform statistical analysis on the collected data. You can calculate averages, standard deviations, percentiles, and other statistical measures to gain insights into the system's behavior. This can help you identify outliers, bottlenecks, and areas for improvement. Comparing datasets. SystemTap allows you to collect data over a period of time and compare multiple datasets. By comparing datasets, you can identify changes in system behavior, track performance improvements or regressions, and validate the effectiveness of optimizations. Profiling. SystemTap provides profiling capabilities that allow you to measure the execution time of specific functions or code blocks. By profiling your code, you can identify performance hotspots and optimize them for better system performance. Real-time performance monitoring. One of the key advantages of SystemTap is its ability to monitor system performance in real time. This means that you can collect and analyze performance data while the system is running, allowing you to identify and address performance issues as they occur. Real-time performance monitoring with SystemTap involves continuously collecting and analyzing performance data, generating alerts or notifications when certain conditions are met, and taking immediate actions to resolve performance issues. This can help you proactively manage system performance and ensure optimal system behavior. To enable real-time performance monitoring with SystemTap, you can run your performance scripts in the background or as daemons. These scripts can be configured to collect data at regular intervals and generate alerts or notifications when specific thresholds are exceeded. By monitoring system performance in real time, you can quickly identify and address performance bottlenecks, ensuring a smooth and efficient system operation. Conclusion. Analyzing system performance is crucial for maintaining a high-performing Linux environment. SystemTap provides a powerful set of tools and a scripting language that allows you to monitor and analyze system performance in real time. By writing custom SystemTap scripts, you can collect data on various system activities, analyze the data, and identify performance bottlenecks. With SystemTap, you can proactively manage system performance and optimize your Linux system for better efficiency and reliability. 6.4 Debugging kernel modules with SystemTap. Kernel modules are an integral part of the Linux operating system, providing additional functionality and extending the capabilities of the kernel. However, debugging kernel modules can be a challenging task due to their privileged nature and the complexity of the kernel itself. In this section, we will explore how to debug kernel modules using SystemTap, a powerful tracing and probing tool for Linux. Understanding kernel modules. Before diving into debugging kernel modules, it is essential to have a basic understanding of what they are and how they work. Kernel modules are pieces of code that can be dynamically loaded and unloaded into the kernel without the need to reboot the system. They can add new features, device drivers, or file systems to the kernel, enhancing its functionality. Kernel modules are written in C and compiled separately from the kernel. They interact with the kernel through a well-defined interface, using functions and data structures provided by the kernel. When a module is loaded, it becomes part of the running kernel, and its code can be executed in the kernel's context. Debugging kernel modules with SystemTap. SystemTap is a powerful tool that allows you to trace and probe the Linux kernel and user space applications. It provides a scripting language and a set of libraries that enable you to write custom scripts to monitor and analyze the behavior of the system. SystemTap can be used to debug kernel modules by inserting probes into the module's code and capturing relevant information during runtime. To debug a kernel module with SystemTap, you need to follow these steps. Install SystemTap. First, you need to install SystemTap on your Linux system. SystemTap is not included in all distributions by default, so you may need to install it from the package manager or compile it from source. Write a SystemTap script. Next, you need to write a SystemTap script that will insert probes into the kernel module's code. The script should define the probes and specify the actions to be taken when the probes are hit. You can use the SystemTap scripting language to define probes based on function names, addresses, or events. Compile the SystemTap script. Once you have written the SystemTap script, you need to compile it using the stap command. The stap command will generate a kernel module that will be loaded into the running kernel. This module will intercept the specified probes and execute the actions defined in the script. Load the SystemTap module. After compiling the SystemTap script, you need to load the generated module into the kernel using the staprun command. This will activate the probes defined in the script and start capturing the specified information. Analyze the captured data. Once the SystemTap module is loaded and the probes are active, you can start analyzing the captured data. SystemTap provides various tools and utilities to process and visualize the captured data, allowing you to gain insights into the behavior of the kernel module. Tips for debugging kernel modules with SystemTap. Debugging kernel modules with SystemTap can be a complex task, but with the right approach, it can be made more manageable. Here are some tips to help you debug kernel modules effectively using SystemTap. Start with simple probes. When starting with SystemTap, it is recommended to begin with simple probes to get familiar with the tool and the debugging process. Start by inserting probes into basic functions or events and gradually increase the complexity as you gain more experience. Use logging and printing. SystemTap allows you to log and print messages during runtime, which can be helpful for debugging purposes. You can use the printf function in your SystemTap script to print messages to the console or log files, providing valuable information about the execution flow of the kernel module. Use conditional probes. SystemTap allows you to define conditional probes that are triggered only when specific conditions are met. This can be useful when you want to capture data only in certain scenarios or when specific variables have specific values. Conditional probes can help you narrow down the scope of your debugging and focus on specific areas of interest. Analyze system performance. SystemTap is not only useful for debugging specific issues but also for analyzing system performance. You can use SystemTap to monitor various system metrics, such as CPU usage, memory usage, disk I/O, and network activity, while the kernel module is running. This can help you identify performance bottlenecks and optimize the module's behavior. Collaborate with the community. Debugging kernel modules can be a challenging task, and it is often helpful to collaborate with the Linux community. There are various forums, mailing lists, and IRC channels where you can seek help and advice from experienced developers and kernel maintainers. Don't hesitate to reach out to the community if you encounter difficulties during the debugging process. By following these tips and leveraging the power of SystemTap, you can effectively debug kernel modules in Linux. SystemTap provides a flexible and powerful framework for tracing and probing the kernel, allowing you to gain insights into the behavior of your modules and diagnose issues more efficiently. In the next section, we will explore another powerful debugging tool for Linux, dtrace, and how it can be used to debug applications and analyze system performance. 7. Debugging with dtrace. 7.1 Introduction to dtrace. dtrace is a powerful dynamic tracing framework that was originally developed for the Solaris operating system and later ported to other Unix-like systems, including Linux. It provides a comprehensive set of tools and features for debugging and analyzing system performance in real time. dtrace allows developers and system administrators to dynamically instrument the kernel and user space applications to gather detailed information about their behavior. What is dtrace? dtrace stands for Dynamic Tracing, and is designed to provide a flexible and efficient way to observe and analyze the behavior of a running system. It allows users to write custom scripts, known as dtrace scripts, which can be dynamically loaded into the kernel or attached to running processes to collect data about various system events and activities. dtrace operates by inserting probes, which are small pieces of code, into the target system. These probes can be placed at specific points in the kernel or user space applications to capture information about function calls, system calls, memory allocations, I/O operations, and other events of interest. The collected data can then be analyzed and visualized to gain insights into system behavior, identify performance bottlenecks, and debug issues. Key features of dtrace. dtrace offers several key features that make it a powerful tool for debugging and performance analysis. Dynamic instrumentation. dtrace allows users to dynamically instrument the kernel and user space applications without requiring any modifications to the source code. This enables developers to gather detailed information about the system's behavior without the need for recompilation or restarting the system. Low overhead. dtrace is designed to have minimal impact on system performance. It achieves this by using lightweight probes and a highly efficient tracing infrastructure. The overhead introduced by dtrace is typically negligible, allowing users to collect data in real time without significantly affecting the system's performance. Scripting language. dtrace provides a powerful scripting language that allows users to write custom scripts to collect and analyze data. The dtrace language is expressive and concise, making it easy to write complex scripts that can extract valuable insights from the collected data. Fine-grained control. dtrace offers fine-grained control over what data to collect and when to collect it. Users can specify the conditions under which probes should be triggered, filter the collected data based on specific criteria, and aggregate the data to generate meaningful statistics and visualizations. Dynamic tracing framework. dtrace provides a comprehensive set of system and user-level probes that cover a wide range of events and activities. These probes can be used to trace function calls, system calls, I/O operations, memory allocations, network activity, and more. Additionally, dtrace allows users to define their own custom probes to instrument specific parts of the system. Safety mechanisms. dtrace is designed with built-in safety mechanisms to prevent scripts from causing harm to the system. It enforces strict access controls and provides a sandboxed environment for executing scripts, ensuring that only authorized users can run dtrace scripts and that they cannot interfere with the normal operation of the system. Use cases for dtrace. dtrace can be used in a wide range of scenarios to debug and analyze system behavior. Some common use cases include performance analysis. dtrace can be used to identify performance bottlenecks in the system by tracing the execution of critical functions, monitoring resource usage, and analyzing system call patterns. It allows users to pinpoint areas of the code that are causing performance degradation and optimize them for better efficiency. Debugging kernel issues. dtrace provides powerful tools for debugging kernel-level issues. It allows users to trace kernel function calls, monitor system calls, and analyze kernel data structures in real time. This can be invaluable for diagnosing and fixing issues related to device drivers, file systems, network protocols, and other kernel components. Application debugging. dtrace can be used to debug user space applications by tracing function calls, monitoring system calls, and analyzing memory usage. It allows users to identify and fix issues such as memory leaks, race conditions, and performance bottlenecks in their applications. Security analysis. dtrace can be used to monitor system activity and detect security vulnerabilities and attacks. It allows users to trace system calls, monitor network traffic, and analyze process behavior to identify suspicious activities and potential security breaches. System monitoring. dtrace can be used as a powerful system monitoring tool. It allows users to collect and analyze various system metrics, such as CPU usage, memory usage, disk I/O, and network activity. This can help in identifying system-wide performance issues, capacity planning, and resource optimization. In the next section, we will explore the process of writing dtrace scripts and how they can be used to gather data and analyze system performance. 7.2 Writing dtrace scripts. dtrace is a powerful dynamic tracing framework that allows you to instrument and analyze the behavior of a running system. It was originally developed for the Solaris operating system but has since been ported to other Unix-like systems, including Linux. Writing dtrace scripts involves using a specialized scripting language called D, which provides a rich set of features for tracing and analyzing system events. Dtrace scripts can be used to monitor various aspects of the system, such as system calls, kernel functions, user-level processes, and even specific applications. Getting started with dtrace. To start writing dtrace scripts, you need to have dtrace installed on your Linux system. Dtrace is not included in the standard Linux distribution, so you may need to install it manually. The dtrace package is typically available in the package repositories of most Linux distributions. Once you have dtrace installed, you can start writing dtrace scripts using a text editor of your choice. Dtrace scripts have a D extension and can be executed using the dtrace command. Anatomy of a dtrace script. A dtrace script consists of several components, including probes, predicates, actions, and aggregations. Let's take a closer look at each of these components. Probes. Probes are the points in the system where dtrace can collect data. Probes can be system-wide or specific to a particular process or application. Dtrace provides a wide range of probes that cover various aspects of the system, such as function entry and exit, system calls, and hardware events. Predicates. Predicates are conditions that determine when a probe should be triggered. Predicates allow you to filter the data collected by dtrace based on specific criteria. For example, you can specify that a probe should only be triggered when a certain function is called with specific arguments. Actions. Actions are the operations that dtrace performs when a probe is triggered. Actions can include printing data to the console, writing data to a file, or executing a command. Dtrace provides a rich set of built-in actions that you can use to perform various tasks. Aggregations. Aggregations allow you to collect and summarize data over time. Aggregations can be used to calculate statistics, such as the average execution time of a function or the number of times a system call is invoked. Dtrace provides several built-in aggregations that you can use to analyze the data collected by your script. Writing your first dtrace script. To illustrate the process of writing a dtrace script, let's consider a simple example. Suppose you want to monitor the system calls made by a specific process. Here's how you can write a dtrace script to achieve this. Syscall, entry PID equals $1 per. Printf process %d called system call %s,n, PID, probe func. In this script, we use the syscall probe, which is triggered whenever a system call is made. The predicate PID equals $1 per ensures that the probe is only triggered for the process specified as an argument when running the script. The action printf prints the process ID and the name of the system call to the console. To run this script, save it to a file with a D extension e.g., syscall_monitor, D, and execute the following command. Sudo dtrace s syscall_monitor, D less than process _id greater than. Replace less than process _id greater than with the ID of the process you want to monitor. When the process makes a system call, you will see the corresponding output on the console. Advanced dtrace scripting. Dtrace provides a wide range of features that allow you to write more complex and powerful scripts. Some of the advanced features include dynamic tracing. Dtrace allows you to dynamically enable and disable probes at runtime. This feature is particularly useful when you want to trace specific events or functions only when certain conditions are met. Scripting language. The D scripting language provides a rich set of features, including variables, loops, conditionals, and functions. This allows you to write more sophisticated scripts that can perform complex analysis and data manipulation. User-level tracing. Dtrace can be used to trace user-level processes and applications. This allows you to monitor the behavior of specific programs and analyze their performance and resource usage. Custom probes. Dtrace allows you to define your own probes, which can be triggered at specific points in your code. This feature is particularly useful when you want to instrument your own applications or libraries for debugging or performance analysis. Conclusion. Writing dtrace scripts is a powerful way to debug and analyze the behavior of a Linux system. With its rich set of features and flexible scripting language, dtrace provides a versatile tool for tracing and monitoring various aspects of the system. By mastering the art of writing dtrace scripts, you can gain deep insights into the inner workings of your Linux system and effectively debug and optimize your applications. 7.3 Analyzing System Performance with dtrace. Dtrace is a powerful dynamic tracing framework that allows you to analyze and diagnose system performance issues in real time. It provides a comprehensive set of tools and features for monitoring and profiling various aspects of the Linux operating system. In this section, we will explore how dtrace can be used to analyze system performance and identify bottlenecks. Understanding system performance analysis. System performance analysis involves monitoring and measuring various system resources and activities to identify performance bottlenecks and optimize system performance. It helps in understanding how the system is utilizing its resources, such as CPU, memory, disk I/O, and network, and identifies areas where improvements can be made. dtrace provides a unique approach to system performance analysis by allowing you to dynamically instrument the kernel and user space applications without the need for recompilation or modification of the code. It enables you to trace and profile system events and activities at a fine-grained level, providing detailed insights into system behavior. dtrace performance analysis tools. dtrace provides a rich set of performance analysis tools that can be used to monitor and analyze system performance. Some of the commonly used dtrace tools for performance analysis are dtrace. The dtrace command is the main interface to the dtrace framework. It allows you to write dscripts that specify what events to trace and how to process the trace data. You can use dtrace to monitor various system activities, such as CPU usage, disk I/O, network traffic, and memory allocation. dtruss. The dtruss command is a dtrace-based system call tracer. It allows you to trace and analyze system calls made by a specific process or all processes on the system. This can be useful for identifying performance bottlenecks caused by excessive system call usage. dtracestat. The dtracestat command provides a summary of system performance statistics collected by dtrace. It displays information about CPU usage, memory usage, disk I/O, and network activity. This can help you quickly identify areas of high resource utilization and potential performance issues. dtrace toolkit. The dtrace toolkit is a collection of dscripts and tools that extend the functionality of dtrace. It provides additional performance analysis tools for monitoring and profiling various system activities, such as file system operations, network protocols, and process behavior. Analyzing CPU usage. One of the key aspects of system performance analysis is understanding CPU usage. dtrace provides several mechanisms to monitor and analyze CPU usage, allowing you to identify processes or threads that are consuming excessive CPU resources. You can use the dtrace command with the N option to specify a dscript that traces CPU-related events. For example, the following dscript traces the CPU provider and prints the process ID and CPU usage for each process. sudo dtrace n. Profile 1001 PID == $target at execname = count. This script uses the profile provider to sample the CPU usage every 1 millisecond. Profile 1001. It then filters the samples based on the process ID PID and counts the number of samples for each process. The results are stored in an associative array at execname and printed at the end. By running this script, you can get a real-time view of the CPU usage for each process on the system. This can help you identify processes that are consuming excessive CPU resources and optimize their performance. Analyzing memory usage. Memory usage is another critical aspect of system performance analysis. dtrace provides several mechanisms to monitor and analyze memory usage, allowing you to identify memory leaks, excessive memory allocations, and inefficient memory usage patterns. You can use the dtrace command with the N option to specify a dscript that traces memory-related events. For example, the following dscript traces the memory provider and prints the memory allocation and deallocation events for each process. sudo dtrace n. fbt. kmalloc. Entry at execname = count fbt. kfree. Entry at execname = count. This script uses the fbt provider to trace the kmalloc and kfree functions, which are used for memory allocation and deallocation in the kernel. It counts the number of events for each process and stores the results in an associative array at execname. By running this script, you can monitor the memory allocation and deallocation events for each process on the system. This can help you identify processes that are allocating or deallocating excessive amounts of memory and optimize their memory usage. Analyzing disk I/O. Disk I/O is a common bottleneck in system performance. dtrace provides several mechanisms to monitor and analyze disk I/O, allowing you to identify processes or files that are causing excessive disk I/O and optimize their performance. You can use the dtrace command with the N option to specify a dscript that traces disk I/O related events. For example, the following dscript traces the EO provider and prints the disk I/O events for each process. sudo dtrace n. EO. Start at execname = count. This script traces all disk I/O events EO, start and counts the number of events for each process. The results are stored in an associative array at execname and printed at the end. By running this script, you can monitor the disk I/O events for each process on the system. This can help you identify processes that are causing excessive disk I/O and optimize their I/O operations. Conclusion. dtrace provides a powerful set of tools and features for analyzing system performance in Linux. By using dtrace, you can monitor and profile various system resources and activities, such as CPU usage, memory usage, disk I/O, and network traffic. This allows you to identify performance bottlenecks, optimize system performance, and improve the overall efficiency of your Linux system. 7.4 Debugging applications with dtrace. dtrace is a powerful dynamic tracing framework that allows you to instrument and analyze the behavior of applications in the operating system in real time. While dtrace is primarily known for its system-level tracing capabilities, it can also be used to debug applications running on Linux. Understanding dtrace. dtrace provides a unique approach to debugging by allowing you to dynamically instrument the code of running applications without the need for recompilation or restarting. It achieves this by inserting probes into the code at runtime, which can be used to collect data and perform analysis. dtrace uses a specialized scripting language called D, which allows you to define probes and specify the actions to be taken when those probes are hit. These actions can include printing values, aggregating data, or even modifying the behavior of the application on the fly. Instrumenting applications. To debug an application with dtrace, you need to identify the areas of interest where you want to collect data. This could be specific function calls, system calls, or even variable values. Once you have identified the areas to instrument, you can define probes using dtrace's scripting language. For example, let's say you want to debug a C program and collect data whenever a specific function is called. You can define a dtrace probe that triggers whenever that function is called and prints out the arguments and return value. You can also add additional actions to collect more data or perform specific analysis. Analyzing application behavior. Once you have instrumented your application with dtrace probes, you can start collecting data and analyzing its behavior. dtrace provides a range of built-in functions and aggregations that allow you to perform complex analysis on the collected data. For example, you can use dtrace to track the frequency of function calls, measure the execution time of specific code paths, or even identify potential bottlenecks in your application. dtrace also allows you to correlate data from different probes, enabling you to gain deeper insights into the behavior of your application. Debugging performance issues. One of the key use cases for dtrace in application debugging is identifying and resolving performance issues. dtrace allows you to trace the execution of your application and collect data on various performance metrics, such as CPU usage, memory allocation, and disk I/O. By analyzing this data, you can pinpoint areas of your application that are causing performance bottlenecks and optimize them accordingly. dtrace also provides the ability to trace system calls and kernel-level events, allowing you to identify any system-level issues that may be impacting the performance of your application. Debugging error conditions. In addition to performance issues, dtrace can also be used to debug error conditions in your application. By instrumenting specific code paths or system calls, you can collect data when an error occurs and analyze it to understand the root cause. For example, if your application is crashing or producing incorrect results, you can use dtrace to trace the execution and collect data at the point of failure. This data can then be used to identify the source of the error, such as a memory corruption or a race condition. Dynamic debugging. One of the unique features of dtrace is its ability to modify the behavior of the application on the fly. Using dtrace, you can dynamically change variables, alter function behavior, or even inject code into the running application. This dynamic debugging capability allows you to experiment with different scenarios and test potential fixes without the need for recompilation or restarting the application. It can be particularly useful when debugging complex issues that are difficult to reproduce or when you need to test the impact of specific changes on the application's behavior. Limitations and considerations. While dtrace provides powerful debugging capabilities, there are some limitations and considerations to keep in mind. First, dtrace requires root or administrative privileges to run, as it operates at a low-level system level. Second, dtrace can introduce some overhead to the system, especially when collecting a large amount of data or performing complex analysis. It's important to carefully select the probes and actions to minimize the impact on the application's performance. Finally, dtrace is not available on all Linux distributions by default. Some distributions may require additional installation steps or configuration changes to enable dtrace support. Conclusion. dtrace is a powerful tool for debugging applications in Linux. Its dynamic tracing capabilities allow you to instrument running applications, collect data, and analyze their behavior in real time. Whether you're debugging performance issues or tracking down error conditions, dtrace provides a flexible and efficient way to gain insights into your application's behavior. 8. Debugging web applications. 8.1 Debugging PHP applications. PHP is a popular programming language for web development, and debugging PHP applications is an essential skill for any web developer. In this section, we will explore various techniques and tools that can help you debug PHP applications effectively in a Linux environment. Understanding PHP debugging. Debugging PHP applications involves identifying and fixing errors, bugs, and performance issues in your code. It allows you to gain insights into the execution flow, variable values, and error messages, helping you pinpoint the root cause of issues and improve the overall quality of your application. PHP provides several built-in features and tools that can assist in the debugging process. These include error reporting, logging, and the ability to set breakpoints and step through code execution. Additionally, there are third-party debugging tools and extensions available that offer more advanced features and capabilities. Enabling error reporting. Error reporting is a fundamental aspect of PHP debugging. By enabling error reporting, you can receive detailed error messages that can help you identify and fix issues in your code. In a development environment, it is recommended to set the error reporting level to the highest value, which includes all types of errors, warnings, and notices. To enable error reporting, you can modify the php.ini configuration file or use the error_reporting function within your PHP code. For example, to enable all error reporting, you can add the following line to your php.ini file. Error_reporting equals e_all. Alternatively, you can use the error_reporting function at the beginning of your PHP script. Error_reporting e_all. By enabling error reporting, PHP will display detailed error messages on the screen or write them to the server's error log file, depending on the configuration. Using debugging tools. In addition to error reporting, there are several debugging tools available for PHP that can greatly assist in the debugging process. These tools provide features such as step-by-step code execution, variable inspection, and stack trace analysis. One popular PHP debugging tool is Xdebug. Xdebug is a powerful extension that integrates with IDEs, integrated development environments, and provides advanced debugging capabilities. It allows you to set breakpoints, step through code execution, inspect variables, and analyze stack traces. Xdebug also provides profiling functionality, which helps identify performance bottlenecks in your code. To use Xdebug, you need to install the extension and configure your PHP environment to enable debugging. The exact installation and configuration steps depend on your Linux distribution and PHP version. Once configured, you can use Xdebug with your preferred IDE to debug PHP applications effectively. Another useful tool for PHP debugging is PHP Debug Bar. PHP Debug Bar is a web-based debugging toolbar that provides real-time information about your PHP application's execution. It displays details such as query times, memory usage, and executed SQL statements. PHP Debug Bar can be easily integrated into your application and helps you monitor and analyze its performance. Logging and debugging statements. Logging is an essential technique for debugging PHP applications. By adding logging statements to your code, you can track the flow of execution, variable values, and error messages. Logging allows you to capture important information during runtime, even in production environments, without interrupting the user experience. PHP provides the error_log function, which allows you to write custom log messages to a specified log file. You can use this function to log important events, variable values, or error messages. For example, error_log user logged in. $username. In addition to the error_log function, you can also use the var_dump and print_r functions to print variable values to the screen or log file. These functions are useful for inspecting the contents of arrays, objects, and other complex data structures. Remote debugging. Remote debugging allows you to debug PHP applications running on a remote server from your local development environment. This is particularly useful when you don't have direct access to the server or when debugging production issues. Xdebug, mentioned earlier, supports remote debugging. To enable remote debugging, you need to configure Xdebug with the appropriate settings in your php.ini file. Once configured, you can connect your IDE to the remote server and start debugging as if the application were running locally. Remote debugging with Xdebug requires a network connection between your local machine and the remote server. It is important to ensure that the necessary ports are open and accessible for the debugging process to work correctly. Conclusion. Debugging PHP applications in a Linux environment is a crucial skill for web developers. By understanding the various debugging techniques and tools available, you can effectively identify and fix issues in your code, improving the overall quality and performance of your PHP applications. Remember to enable error reporting, use debugging tools like Xdebug, and leverage logging and remote debugging capabilities to streamline your debugging process. 8.2 Debugging Node.js applications. Node.js is a popular runtime environment for building server-side applications using JavaScript. It provides a powerful and scalable platform for developing web applications, APIs, and other networked services. However, like any software, Node.js applications can have bugs and issues that need to be debugged and resolved. In this section, we will explore various techniques and tools for debugging Node.js applications in a Linux environment. We will cover both basic and advanced debugging techniques to help you effectively identify and fix issues in your Node.js code. Understanding Node.js debugging. Before diving into the debugging process, it's important to understand how Node.js applications are executed and how debugging works in this environment. Node.js uses the V8 JavaScript engine, which provides built-in debugging capabilities through the Chrome Developer Tools Protocol (CDP). When a Node.js application is started in debug mode, it listens for incoming debugging connections on a specified port. This allows you to connect a debugger, such as the Chrome DevTools or a command line debugger, to the running Node.js process. Once connected, you can set breakpoints, inspect variables, and step through the code to identify and fix issues. Setting up the debugging environment. To start debugging a Node.js application, you need to enable the debugging mode by passing the inspect flag when starting the application. For example, node inspect index.js. This will start the Node.js application in debug mode and listen for debugging connections on the default port 9229. You can also specify a different port by using the inspect equals less than port greater than flag. Debugging with Chrome DevTools. One of the most popular tools for debugging Node.js applications is the Chrome DevTools. It provides a comprehensive set of debugging features, including breakpoints, step-by-step execution, variable inspection, and performance profiling. To debug a Node.js application using Chrome DevTools, follow these steps. Start your Node.js application in debug mode using the inspect flag. Open Google Chrome and navigate to. Under the Remote Target section, you should see your Node.js application listed. Click the Inspect button to open the DevTools. The DevTools window will open, showing the Node.js application's source code. You can set breakpoints by clicking on the line numbers or using the debugger statement in your code. Once a breakpoint is hit, you can inspect variables, step through the code, and analyze the application's state. Debugging with command line debuggers. In addition to graphical tools like Chrome DevTools, there are also command line debuggers available for debugging Node.js applications. These debuggers provide a lightweight and efficient way to debug your code without the need for a graphical interface. One popular command line debugger for Node.js is Node Inspect, which is built in with Node.js. To use it, follow these steps. Start your Node.js application in debug mode using the inspect flag. Open a terminal and navigate to the directory where your Node.js application is located. Run the command node inspect index.js to start the debugger. The debugger will start and pause at the first line of your code. You can use commands like con to continue execution, next to step to the next line, and repl to enter a REPL session to inspect variables and execute code. Advanced debugging techniques. While breakpoints and step-by-step execution are useful for identifying issues in your code, Node.js provides additional debugging techniques for more complex scenarios. One such technique is the use of the inspect brk flag, which stops the execution of your code at the very beginning. This allows you to set breakpoints before any code is executed, which can be helpful for debugging initialization or startup issues. Another advanced debugging technique is the use of conditional breakpoints. Instead of stopping at every occurrence of a breakpoint, you can specify a condition that must be met for the breakpoint to be triggered. This can be useful for debugging specific scenarios or when dealing with large datasets. Conclusion. Debugging Node.js applications in a Linux environment is an essential skill for any developer. By understanding the debugging process, setting up the debugging environment, and using the right tools and techniques, you can effectively identify and fix issues in your Node.js code. In this section, we explored the basics of debugging Node.js applications using tools like Chrome DevTools and command line debuggers. We also discussed advanced debugging techniques such as conditional breakpoints and the use of the inspect brk flag. With these techniques and tools at your disposal, you can confidently debug and resolve issues in your Node.js applications, ensuring they run smoothly and efficiently. 8.3 Debugging Ruby on Rails applications. Ruby on Rails is a popular web application framework written in the Ruby programming language. It provides developers with a powerful and efficient way to build web applications. However, like any software, Ruby on Rails applications can have bugs and issues that need to be debugged. In this section, we will explore some common debugging techniques and tools specifically tailored for Ruby on Rails applications in a Linux environment. Understanding Ruby on Rails debugging. Debugging Ruby on Rails applications involves identifying and fixing issues that may arise during the development or deployment process. These issues can range from syntax errors and logical bugs to performance bottlenecks and database connectivity problems. Effective debugging requires a systematic approach and the use of appropriate tools. Logging and debugging statements. One of the simplest and most effective ways to debug Ruby on Rails applications is by using logging and debugging statements. Ruby on Rails provides a built-in logging mechanism that allows developers to output messages to log files. By strategically placing logging statements throughout the code, developers can track the flow of execution and identify potential issues. For example, the logger debug method can be used to output debug messages to the log file. These messages can include variable values, method calls, and other relevant information. By analyzing the log files, developers can gain insights into the application's behavior and identify any unexpected or incorrect behavior. Debugging tools. In addition to logging, there are several debugging tools available for Ruby on Rails applications in a Linux environment. These tools provide advanced features and capabilities to help developers diagnose and fix issues more efficiently. Some popular debugging tools for Ruby on Rails include Pry. Pry is a powerful interactive shell and debugger for Ruby. It allows developers to pause the execution of their code at any point and interactively explore the state of the application. Pry provides features such as code introspection, variable inspection, and the ability to modify code on the fly. It can be integrated into Ruby on Rails applications to provide a more interactive and dynamic debugging experience. Debug. Debug is a fast and simple debugger for Ruby. It allows developers to set breakpoints in their code and step through the execution line by line. Debug provides a command line interface with commands for navigating the code, inspecting variables, and evaluating expressions. It can be used to debug Ruby on Rails applications by adding breakpoints to specific parts of the code and analyzing the state of the application at those breakpoints. Better errors. Better errors is a gem that provides a better error page for Ruby on Rails applications. When an error occurs, Better Errors replaces the default error page with a more informative and interactive page. It includes a stack trace, local and instance variable inspection, and a REPL read eval print loop console for executing code in the context of the error. Better Errors can be a valuable tool for quickly diagnosing and fixing errors in Ruby on Rails applications. Bullet. Bullet is a gem that helps identify and optimize N+1 query issues in Ruby on Rails applications. N+1 queries occur when an application makes multiple database queries instead of using eager loading. This can lead to performance issues, especially when dealing with large datasets. Bullet analyzes the queries made by the application and provides suggestions for optimizing them. It can be used to identify and fix N+1 query issues, improving the overall performance of Ruby on Rails applications. Debugging techniques. When debugging Ruby on Rails applications, it is important to follow a systematic approach to identify and fix issues effectively. Here are some techniques that can help in the debugging process. Reproducing the issue. The first step in debugging is to reproduce the issue consistently. This involves identifying the steps or conditions that trigger the problem. By understanding how to reproduce the issue, developers can isolate the problematic code and focus their debugging efforts. Analyzing error messages. Error messages provide valuable information about the nature of the issue. When an error occurs, it is important to carefully read and analyze the error message. The error message often includes a stack trace, which shows the sequence of method calls leading to the error. By analyzing the stack trace, developers can identify the specific line of code causing the issue. Using breakpoints. Breakpoints are markers placed in the code that pause the execution of the application at a specific point. By setting breakpoints at strategic locations, developers can inspect the state of the application and track the flow of execution. Breakpoints can be set using debugging tools like prior bybug, allowing developers to step through the code and analyze the behavior of the application. Inspecting variables. Inspecting variables is a crucial part of debugging. By examining the values of variables at different points in the code, developers can gain insights into the state of the application. Debugging tools like pry and bybug provide commands for inspecting variables, allowing developers to view their values and track changes. Testing and refactoring. Once an issue has been identified and fixed, it is important to test the application thoroughly to ensure that the problem has been resolved. Writing automated tests can help catch regressions and prevent similar issues from occurring in the future. Additionally, refactoring the code to improve its structure and readability can help prevent future bugs and make the debugging process easier. Conclusion. Debugging Ruby on Rails applications in a Linux environment requires a combination of techniques, tools, and a systematic approach. By using logging and debugging statements, leveraging debugging tools like pry and bybug, and following effective debugging techniques, developers can identify and fix issues more efficiently. Debugging is an essential skill for any Ruby on Rails developer, and mastering it can greatly improve the quality and reliability of web applications. 8.4 Debugging Python Web Applications. Python is a popular programming language for web development, and debugging Python web applications is an essential skill for any developer. In this section, we will explore various techniques and tools that can help you effectively debug Python web applications running on a Linux environment. Understanding the debugging process. Before diving into the specific tools and techniques, it's important to understand the general debugging process for Python web applications. The debugging process typically involves the following steps. Identifying the issue. The first step in debugging is to identify the problem or issue in your Python web application. This could be a functional bug, a performance issue, or an error that is causing the application to crash. Reproducing the issue. Once you have identified the problem, the next step is to reproduce the issue consistently. This involves understanding the steps or conditions that lead to the problem occurring. Isolating the issue. After reproducing the issue, it's important to isolate the problem to a specific part of your code or system. This helps in narrowing down the root cause and makes the debugging process more efficient. Analyzing the code. Once the issue is isolated, you need to analyze the code to understand why the problem is occurring. This involves examining the relevant code sections, variables, and data structures to identify any logical errors or unexpected behavior. Using debugging tools. Debugging tools play a crucial role in the debugging process. These tools provide features like breakpoints, stepping through code, inspecting variables, and capturing stack traces, which help in understanding the flow of execution and identifying the cause of the issue. Fixing the issue. Once the root cause is identified, you can proceed to fix the issue by making the necessary code changes or configuration adjustments. Debugging Python web applications. Python web applications are typically built using web frameworks like Django, Flask, or Pyramid. These frameworks provide their own debugging mechanisms, which can be used to debug web applications running on a Linux environment. Here are some common techniques and tools for debugging Python web applications. Logging. Logging is a fundamental technique for debugging Python web applications. By strategically placing log statements in your code, you can track the flow of execution, capture variable values, and identify any unexpected behavior. Python's built-in logging module provides a flexible and powerful logging framework that can be customized to suit your debugging needs. Debugging with PDB. Python's built-in PDB module is a powerful interactive debugger that allows you to step through your code, set breakpoints, and inspect variables. You can use PDB to debug your Python web application by adding breakpoints at specific locations in your code and running the application in debug mode. Remote debugging. Remote debugging allows you to debug a Python web application running on a remote server from your local development environment. Tools like PyDev and PTVSD provide remote debugging capabilities for Python web applications. By connecting your local debugger to the remote server, you can step through the code, inspect variables, and analyze the application's behavior. Profiling. Profiling is a technique used to analyze the performance of your Python web application. Profiling tools like cprofile and line_profiler help you identify performance bottlenecks, memory leaks, and areas of code that can be optimized. By profiling your application, you can gain insights into its runtime behavior and make informed decisions to improve its performance. Debugging with IDEs. Integrated development environments (IDEs) like PyCharm, Visual Studio Code, and Eclipse provide powerful debugging features specifically designed for Python web applications. These IDEs offer features like breakpoints, step-by-step execution, variable inspection, and stack trace analysis, making the debugging process more intuitive and efficient. Error handling and exception tracking. Proper error handling and exception tracking are essential for debugging Python web applications. By implementing robust error handling mechanisms and using tools like Sentry or Rollbar, you can capture and track exceptions that occur in your application. These tools provide detailed error reports, stack traces, and contextual information, which can help you quickly identify and fix issues. In addition to these techniques, it's important to have a good understanding of the underlying web framework and its debugging capabilities. Most web frameworks provide detailed documentation and resources on debugging techniques specific to their framework. By leveraging these resources, you can effectively debug your Python web applications and ensure their smooth operation. Remember, debugging is an iterative process, and it requires patience and persistence. By following a systematic approach, using the right tools, and continuously improving your debugging skills, you can become proficient in debugging Python web applications running on a Linux environment. 9. Debugging embedded Linux systems. 9.1 Introduction to Embedded Linux Debugging. Embedded Linux systems are widely used in various industries, including automotive, aerospace, consumer electronics, and industrial automation. These systems are designed to perform specific tasks and are often deployed in resource-constrained environments. Debugging issues in embedded Linux systems can be challenging due to limited resources, real-time requirements, and the absence of a traditional user interface. In this section, we will explore the fundamentals of embedded Linux debugging and discuss various techniques and tools that can help in identifying and resolving issues. Understanding embedded Linux debugging. Embedded Linux debugging involves the process of identifying and fixing software and hardware issues in an embedded Linux system. These issues can range from software bugs and crashes to hardware malfunctions and performance bottlenecks. The goal of debugging is to locate the root cause of the problem and implement a solution to ensure the system functions as intended. Embedded Linux systems often have limited resources, such as memory, processing power, and storage. These constraints make debugging more challenging as traditional debugging techniques may not be feasible. Additionally, embedded systems are often deployed in real-time environments where timing is critical. Debugging in such scenarios requires careful consideration of the impact on system performance and responsiveness. Debugging boot issues. One common area of concern in embedded Linux systems is boot-related issues. When a system fails to boot properly, it can be challenging to identify the cause of the problem. In such cases, it is essential to have a good understanding of the boot process and the various components involved. Debugging boot issues typically involves analyzing the bootloader, kernel, and initial RAM disk initard configuration. By examining the bootloader configuration, you can verify if the correct kernel and initard are being loaded. Additionally, examining the kernel logs can provide valuable information about any errors or warnings encountered during the boot process. To debug boot issues, you can use tools like U-Boot, which is a popular bootloader used in many embedded Linux systems. U-Boot provides features like interactive debugging, memory inspection, and script execution, which can help in diagnosing boot-related problems. Debugging hardware interactions. Embedded Linux systems often interact with various hardware components, such as sensors, actuators, and communication interfaces. Debugging issues related to hardware interactions requires a combination of software and hardware debugging techniques. One approach to debugging hardware interactions is to use hardware debugging tools like JTAG, Joint Test Action Group, or SWD, Serial Wire Debug. These tools allow you to connect to the embedded system's processor and inspect its internal state. By setting breakpoints and stepping through the code, you can identify any issues related to hardware interactions. Another technique is to use software debugging tools that provide access to hardware-specific registers and interfaces. For example, the Linux kernel provides the SYSFS interface, which allows you to access and modify hardware-specific settings. By examining the values of these registers and interfaces, you can gain insights into the behavior of the hardware components and identify any potential issues. Debugging real-time systems. Embedded Linux systems often operate in real-time environments where timing is critical. Real-time systems require precise control over task scheduling and response times to meet strict deadlines. Debugging real-time systems involves identifying and resolving issues that can impact the system's ability to meet these timing requirements. One common challenge in debugging real-time systems is identifying and resolving timing-related issues, such as missed deadlines or excessive latencies. Tools like RT-tests and LatencyTop can help in measuring and analyzing the system's real-time performance. By identifying tasks with high latencies or missed deadlines, you can pinpoint the areas that require optimization or bug fixing. Another aspect of debugging real-time systems is analyzing the impact of interrupts and context switches on system performance. Tools like perf and ltrace can provide insights into the timing behavior of interrupts and context switches, allowing you to identify any issues that may affect real-time performance. In conclusion, debugging embedded Linux systems requires a combination of software and hardware debugging techniques. Understanding the boot process, debugging hardware interactions, and addressing real-time requirements are essential aspects of embedded Linux debugging. By utilizing the appropriate tools and techniques, developers can effectively identify and resolve issues in embedded Linux systems, ensuring their proper functioning in resource-constrained and real-time environments. 9.2 Debugging boot issues. When it comes to debugging boot issues in Linux, it can be a challenging task due to the complexity of the boot process and the various components involved. Boot issues can range from a system not starting up at all to specific errors or failures during the boot process. In this section, we will explore some common techniques and tools that can help you diagnose and resolve boot issues in Linux. Understanding the boot process. Before diving into the debugging techniques, it is essential to have a basic understanding of the Linux boot process. The boot process consists of several stages, including the BIOS UEFI initialization, bootloader execution, kernel loading, and initialization of system services. Each stage plays a crucial role in the successful booting of the system. During the boot process, various components such as the BIOS UEFI firmware, bootloader such as grub or lilo kernel, and init system such as systemd or sysv init work together to bring the system to a fully operational state. Any issues or failures in any of these stages can result in a failed or problematic boot. Troubleshooting boot issues. When faced with a boot issue, the first step is to identify the specific stage at which the problem occurs. This can be done by observing any error messages or abnormal behavior during the boot process. Once you have identified the stage, you can then proceed with the appropriate debugging techniques. 1. BIOS UEFI initialization issues. If the system fails to start up or hangs during the BIOS UEFI initialization stage, it could indicate a hardware problem or a misconfiguration in the BIOS UEFI settings. In such cases, you can try the following steps. Check the hardware connections and ensure that all components are properly seated. Reset the BIOS UEFI settings to their default values. Update the BIOS UEFI firmware to the latest version if available. 2. Bootloader issues. If the bootloader fails to load or presents an error message, it is crucial to investigate the bootloader configuration and settings. Here are some steps you can take. Check the bootloader configuration file e.g., etc. default grub for any misconfigurations or incorrect settings. Verify that the bootloader is pointing to the correct kernel and initramps files. Ensure that the bootloader is installed correctly in the master boot record (MBR) or FE system partition, especially of the boot device. 3. Kernel loading issues. If the kernel fails to load or encounters errors during the boot process, it is necessary to investigate the kernel configuration and parameters. Here are some steps you can follow. Check the kernel command line parameters passed by the bootloader. These parameters can be found in the bootloader configuration file. Enable kernel debugging options such as debugger verbose to get more detailed information during the boot process. Examine the kernel log messages by accessing the system logs var log messages or var log syslog or using the dmesg command. 4. Init system issues. If the system fails to initialize the init system or encounters errors during the initialization process, it is essential to investigate the init system configuration and services. Here are some steps you can take. Check the init system configuration files e.g., etc. initub for sysv init or etc. systemd, system for any misconfigurations or incorrect settings. Verify that the required system services are starting correctly and not encountering any errors. Examine the init system logs var log messages or var log syslog for any error messages related to the initialization process. Debugging tools for boot issues. In addition to the troubleshooting techniques mentioned above, several tools can assist in debugging boot issues in Linux. These tools provide insights into the boot process and help identify the root cause of the problem. Some commonly used tools include dmesg. This command displays the kernel ring buffer, which contains information about the boot process and any error messages encountered. journalctl. This command provides access to the systemd journal, which contains detailed logs of the system's activities, including the boot process. Strace. This tool allows you to trace system calls and signals, which can be helpful in identifying issues with specific processes or system services during the boot process. Systemd analyze. This command provides information about the system's boot time, including the time taken by each service to start up. Boot chart. This tool generates a graphical representation of the boot process, allowing you to visualize the time taken by each component. Conclusion. Debugging boot issues in Linux requires a systematic approach and a good understanding of the boot process. By following the troubleshooting techniques mentioned in this section and utilizing the appropriate tools, you can effectively diagnose and resolve boot problems in your Linux system. Remember to document your findings and share them with the Linux community to contribute to the collective knowledge of debugging boot issues. 9.3 Debugging hardware interactions. Debugging hardware interactions in Linux can be a challenging task, as it involves troubleshooting issues related to the interaction between the software and the underlying hardware components. Hardware interactions can include device drivers, input-output operations, interrupts, and other low-level operations that directly interact with the hardware. When debugging hardware interactions, it is important to have a good understanding of the hardware architecture and how the software interacts with it. This knowledge will help you identify and resolve issues more effectively. In this section, we will explore some common techniques and tools that can be used to debug hardware interactions in Linux. 9.3.1 Understanding hardware interactions. Before diving into the debugging process, it is crucial to have a clear understanding of how hardware interactions work in Linux. Hardware interactions involve communication between the software and various hardware components such as processors, memory, input-output devices, and buses. These interactions are facilitated by device drivers, which act as intermediaries between the software and the hardware. Device drivers provide an interface for the software to communicate with the hardware. They handle low-level operations such as reading from and writing to hardware registers, handling interrupts, and managing data transfer between the software and the hardware. When debugging hardware interactions, it is important to focus on the device drivers that are involved in the specific hardware operation. 9.3.2 Debugging techniques for hardware interactions. When debugging hardware interactions in Linux, there are several techniques that can be employed to identify and resolve issues. Here are some commonly used techniques. 1. Logging and tracing. Logging and tracing are essential techniques for debugging hardware interactions. By enabling logging and tracing mechanisms, you can capture detailed information about the software's interaction with the hardware. This information can include function calls, data transfers, and error messages. By analyzing the logs and traces, you can identify potential issues and pinpoint the source of the problem. 2. Hardware debugging tools. Hardware debugging tools can be invaluable when debugging hardware interactions. These tools allow you to monitor and analyze the behavior of the hardware in real time. They can provide insights into the timing of hardware operations, register values, and other low-level details. Some commonly used hardware debugging tools include logic analyzers, oscilloscopes, and JTAG debuggers. 3. Kernel debugging. Kernel debugging can be useful when debugging hardware interactions that involve device drivers or kernel-level operations. By enabling kernel debugging, you can capture detailed information about the kernel's interaction with the hardware. This information can include function calls, interrupt handling, and data transfers. Kernel debugging tools such as KGDB and kprobes can be used to analyze the kernel's behavior and identify potential issues. 4. Hardware simulation. In some cases, it may be difficult to reproduce hardware-related issues in a development environment. In such situations, hardware simulation can be a useful technique. Hardware simulation involves creating a virtual representation of the hardware environment, allowing you to simulate various hardware interactions. By simulating the hardware, you can reproduce and debug issues without the need for physical hardware. 9.3.3 Debugging tools for hardware interactions. In addition to the debugging techniques mentioned above, there are several tools available in Linux that can aid in debugging hardware interactions. Here are some commonly used tools. 1. LTTNG. LTTNG, Linux Trace Toolkit Next Generation, is a powerful tracing framework for Linux. It allows you to trace and analyze various aspects of the system, including hardware interactions. LTTNG provides detailed information about function calls, interrupts, and data transfers, which can be invaluable when debugging hardware-related issues. 2. Perf. Perf is a performance analysis tool in Linux that can also be used for debugging hardware interactions. It provides a wide range of features, including hardware event-based sampling, tracing, and profiling. Perf can help you identify performance bottlenecks and analyze the behavior of the hardware during software execution. 3. Strace. Strace is a system call tracer that can be used to debug hardware interactions at the system call level. It allows you to trace the system calls made by a program and analyze the interaction between the software and the underlying hardware. Strace can provide insights into file operations, network communication, and other low-level interactions. 4. GDB. GDB, New Debugger, is a powerful debugging tool that can be used for debugging hardware interactions in Linux. It allows you to analyze the behavior of the software and the interaction with the hardware at a low level. GDB provides features such as breakpoints, watchpoints, and memory inspection, which can help you identify and resolve hardware-related issues. Conclusion. Debugging hardware interactions in Linux requires a good understanding of the hardware architecture and the software's interaction with it. By employing the right techniques and tools, such as logging and tracing, hardware debugging tools, kernel debugging, and hardware simulation, you can effectively identify and resolve hardware-related issues. Additionally, tools like ltrace, perf, strace, and GDB can provide valuable insights into the behavior of the software and the underlying hardware. With these techniques and tools at your disposal, you can master the art of debugging hardware interactions in Linux. 9.4 Debugging real-time systems. Real-time systems are designed to respond to events within strict time constraints. These systems are commonly used in industries such as aerospace, automotive, and industrial automation, where timing accuracy is critical. Debugging real-time systems can be challenging due to the need for precise timing and the potential for unpredictable behavior. In this section, we will explore some common debugging techniques and strategies for real-time systems in Linux. We will discuss tools and approaches that can help identify and resolve issues related to timing, synchronization, and performance. Understanding real-time systems. Before diving into debugging techniques, it is important to have a basic understanding of real-time systems. Real-time systems are classified into two categories: hard real-time and soft real-time. Hard real-time systems have strict timing requirements, and missing a deadline can have severe consequences. Examples of hard real-time systems include flight control systems and medical devices. Soft real-time systems, on the other hand, have timing constraints, but missing a deadline may not have catastrophic consequences. Examples of soft real-time systems include multimedia applications and video games. Debugging techniques for real-time systems. When debugging real-time systems, it is crucial to minimize the impact on timing and performance. Here are some techniques that can help in the debugging process. 1. Logging and tracing. Logging and tracing are essential techniques for understanding the behavior of real-time systems. By logging relevant information and tracing the execution flow, you can gain insights into the system's behavior and identify potential issues. In Linux, you can use tools like syslog or dmesg to capture system logs. Additionally, you can incorporate logging statements in your code to track the execution flow and record important events. However, it is important to note that excessive logging can impact system performance, so it should be used judiciously. 2. Timing analysis. Timing analysis is crucial for identifying timing-related issues in real-time systems. By analyzing the timing behavior of your system, you can identify potential bottlenecks, race conditions, or missed deadlines. Tools like perf and ltrace in Linux can help you analyze the timing behavior of your system. These tools provide insights into the execution time of functions, system calls, and interrupts. By analyzing this data, you can identify areas where the system is spending excessive time or where timing constraints are not being met. 3. Synchronization and locking. Real-time systems often involve multiple tasks or threads that need to synchronize their actions. Issues related to synchronization and locking can lead to race conditions, deadlocks, or priority inversion. To debug synchronization issues, you can use tools like strace or ltrace to trace system calls and library calls. These tools can help you identify potential issues with locking, resource allocation, or inter-process communication. 4. Performance monitoring. Monitoring the performance of your real-time system is crucial for identifying performance bottlenecks and optimizing system behavior. Tools like top, htop, and SAR can provide real-time insights into system resource usage, CPU utilization, memory usage, and disk I/O. By monitoring system performance, you can identify areas where the system is underutilized or overloaded. This information can help you optimize the system's behavior and ensure that timing constraints are met. 5. Debugging tools for real-time systems. In addition to the general-purpose debugging tools available in Linux, there are specific tools and frameworks designed for debugging real-time systems. Some popular tools include RTAI, Real-Time Application Interface. RTAI is a popular real-time extension for Linux that provides a real-time environment for developing and debugging real-time applications. LTTNG, Linux Trace Toolkit. Next Generation. LTTNG is a powerful tracing framework for Linux that allows you to trace and analyze the behavior of your real-time system. GDB, New Debugger. GDB is a versatile debugger that can be used for debugging real-time systems. It supports features like remote debugging, which allows you to debug a real-time system running on a remote target. Conclusion. Debugging real-time systems in Linux requires a deep understanding of the system's timing requirements and behavior. By using techniques like logging, timing analysis, synchronization analysis, and performance monitoring, you can identify and resolve issues related to timing, synchronization, and performance. In addition to the general-purpose debugging tools available in Linux, there are specific tools and frameworks designed for debugging real-time systems. These tools provide additional capabilities and insights into the behavior of real-time systems. Remember that debugging real-time systems can be challenging, and it is important to minimize the impact on timing and performance during the debugging process. With the right tools and techniques, you can effectively debug and optimize the behavior of your real-time system. 10. Debugging security issues. 10.1 Debugging privilege escalation vulnerabilities. Privilege escalation vulnerabilities are a serious security concern in any operating system, including Linux. These vulnerabilities allow an attacker to gain elevated privileges and access sensitive information or perform unauthorized actions on a system. As a Linux developer or administrator, it is crucial to understand how to identify and debug privilege escalation vulnerabilities to ensure the security of your system. Understanding privilege escalation vulnerabilities. Privilege escalation vulnerabilities occur when a user or process gains higher privileges than intended. This can happen due to programming errors, misconfigurations, or flaws in the system's security mechanisms. Attackers exploit these vulnerabilities to bypass access controls and gain unauthorized access to resources or execute malicious code with elevated privileges. To effectively debug privilege escalation vulnerabilities, it is essential to understand the common types of vulnerabilities that can lead to privilege escalation. Buffer overflows. Buffer overflows occur when a program writes data beyond the allocated memory buffer, overwriting adjacent memory locations. Attackers can exploit this vulnerability to overwrite critical data structures or inject malicious code into the program's execution flow. Insecure file permissions. Insecure file permissions allow unauthorized users to read, write, or execute files that they should not have access to. Attackers can exploit this vulnerability to modify critical system files or execute arbitrary code with elevated privileges. Insecure configuration settings. Misconfigurations in system settings or application configurations can lead to privilege escalation vulnerabilities. For example, granting excessive privileges to a user or service or allowing insecure remote access can provide attackers with unauthorized access to sensitive resources. Insecure input validation. Failure to properly validate user input can lead to privilege escalation vulnerabilities. Attackers can exploit this vulnerability by injecting malicious input that bypasses security checks and allows them to execute arbitrary code with elevated privileges. Debugging privilege escalation vulnerabilities. Debugging privilege escalation vulnerabilities in Linux involves identifying the root cause of the vulnerability and implementing appropriate fixes. Here are some steps to help you debug privilege escalation vulnerabilities effectively. Identify the vulnerable code. Start by analyzing the code or system configuration where the vulnerability exists. This may involve reviewing source code, configuration files, or system logs to identify potential areas of concern. Reproduce the vulnerability. Once you have identified the vulnerable code, try to reproduce the privilege escalation vulnerability in a controlled environment. This may involve crafting specific inputs or executing certain actions to trigger the vulnerability. Use debugging tools. Debugging tools like GDB, new debugger, can be invaluable in analyzing the vulnerable code and understanding its behavior. Use breakpoints, watchpoints, and other debugging features to step through the code and identify the point at which the privilege escalation occurs. Analyze memory corruption. If the vulnerability is due to a buffer overflow or memory corruption, use tools like Valgrind or Address Sanitizer to detect memory errors and analyze the memory layout during program execution. These tools can help identify the specific memory locations that are being overridden and potentially exploited. Review access controls. Check the access controls and permissions associated with the vulnerable code or system configuration. Ensure that only authorized users or processes have the necessary privileges to access critical resources. Adjust permissions as needed to mitigate the vulnerability. Implement security patches. If the vulnerability is due to a known issue or software bug, check for security patches or updates provided by the software vendor. Apply these patches to fix the vulnerability and prevent future exploitation. Perform security audits. Regularly audit your system for privilege escalation vulnerabilities. Use tools like OpenSCAP or Linux to scan for misconfigurations, insecure file permissions, or other security weaknesses. Address any identified vulnerabilities promptly. Follow security best practices. Implement security best practices such as the principle of least privilege, secure coding practices, and regular security updates. Stay informed about the latest security threats and vulnerabilities in Linux and take proactive measures to protect your system. By following these steps and staying vigilant about security, you can effectively debug privilege escalation vulnerabilities in Linux and ensure the integrity and security of your system. Remember that debugging is an ongoing process, and it is essential to regularly review and update your security measures to stay ahead of potential threats. 10.2 Debugging buffer overflows. Buffer overflow is a common vulnerability that can be exploited by attackers to gain unauthorized access to a system or execute malicious code. It occurs when a program writes data beyond the allocated memory buffer, overwriting adjacent memory locations. This can lead to unpredictable behavior, crashes, and potential security breaches. Debugging buffer overflows in Linux requires a thorough understanding of the underlying causes and techniques to identify and fix these vulnerabilities. In this section, we will explore various debugging strategies and tools that can help in detecting and resolving buffer overflow issues. Understanding buffer overflows. Before diving into the debugging process, it is essential to understand how buffer overflows occur and their potential impact on a system. Buffer overflows typically happen when a program does not properly validate the size of input data before copying it into a fixed size buffer. This can result in the overwriting of adjacent memory locations, including critical data and program instructions. Buffer overflows can be categorized into two types, stack-based and heap-based. In stack-based buffer overflows, the vulnerable buffer is located on the stack, while in heap-based buffer overflows, the vulnerable buffer is allocated on the heap. Detecting buffer overflows. Detecting buffer overflows can be challenging, as they often manifest as unexpected crashes or erratic behavior. However, there are several techniques and tools available to help identify buffer overflow vulnerabilities. One common approach is to use a debugger, such as GDB, new debugger, to analyze the program's behavior and identify the point of failure. By setting breakpoints and examining the program's memory state, you can trace the execution flow and identify any buffer overflow occurrences. Another useful tool for detecting buffer overflows is Address Sanitizer, ASAN, a memory error detector developed by Google. ASAN can be used to instrument the program during compilation, adding runtime checks for buffer overflows and other memory errors. When a buffer overflow occurs, ASAN will report the issue, including the location and size of the overflow. Fixing buffer overflows. Once a buffer overflow has been detected, it is crucial to fix the vulnerability to prevent potential security breaches. The following are some common techniques for fixing buffer overflows. Input validation. Ensure that all input data is properly validated and sanitized before copying it into a buffer. This includes checking the size of the input data and ensuring it does not exceed the buffer's capacity. Bounds checking. Implement bounds checking to ensure that data is not written beyond the allocated buffer. This can be achieved by using safe string manipulation functions, such as strncpy instead of stringcopy, which allows specifying the maximum number of characters to copy. Stack canaries. Stack canaries are values placed between the buffer and the return address on the stack. They act as a guard against buffer overflows by checking if the canary value has been modified before returning from a function. If the canary value has changed, it indicates a buffer overflow has occurred, and the program can terminate or take appropriate action. Address space layout randomization, ASLR. ASLR is a security technique that randomizes the memory layout of a program, making it harder for attackers to exploit buffer overflows. By randomizing the location of critical memory areas, such as the stack and heap, ASLR can mitigate the impact of buffer overflow vulnerabilities. Debugging buffer overflows with GDB. GDB is a powerful debugger that can be used to analyze and debug buffer overflow vulnerabilities. Here are some steps to debug buffer overflows using GDB. Compile the program with debugging symbols enabled. This can be done by adding the G flag to the compiler command. Start GDB by running GDB less than program greater than in the terminal, where less than program greater than is the name of the executable. Set a breakpoint at the suspected location of the buffer overflow using the break command. For example, break main sets a breakpoint at the beginning of the main function. Run the program using the run command. GDB will stop at the breakpoint, allowing you to examine the program's memory state. Use GDB commands such as print and x to inspect the values of variables and memory locations. This can help identify any buffer overflow occurrences. If a buffer overflow is detected, analyze the code to determine the cause of the vulnerability. Look for instances where input data is copied into fixed-size buffers without proper bounds checking. Implement the necessary fixes, such as input validation and bounds checking, to prevent buffer overflows. Test the program again to ensure that the buffer overflow vulnerability has been successfully resolved. By following these steps and leveraging the power of GDB, you can effectively debug and fix buffer overflow vulnerabilities in your Linux programs. Conclusion. Buffer overflows are a significant security concern in Linux systems, as they can lead to unauthorized access and code execution. Understanding the causes and techniques for detecting and fixing buffer overflows is crucial for ensuring the security and stability of your applications. By using tools like GDB and following best practices, you can effectively debug and resolve buffer overflow vulnerabilities in your Linux programs. 10.3 Debugging code injection attacks. Code injection attacks are a common type of security vulnerability that can have serious consequences for a system. In a code injection attack, an attacker is able to insert malicious code into a target system, which is then executed by the system. This can lead to unauthorized access, data breaches, and other security issues. Detecting and debugging code injection attacks in a Linux environment is crucial for maintaining the security and integrity of a system. In this section, we will explore some techniques and tools that can be used to identify and debug code injection attacks in Linux. Understanding code injection attacks. Before we dive into the debugging techniques, it's important to have a clear understanding of how code injection attacks work. Code injection attacks typically exploit vulnerabilities in a system's input validation mechanisms. Attackers can inject malicious code into a system by manipulating user input, such as through web forms, command line arguments, or network protocols. Once the malicious code is injected, it can be executed by the system, leading to various security risks. Common types of code injection attacks include SQL injection, command injection, and remote code execution. Identifying code injection attacks. Detecting code injection attacks can be challenging, as they often involve subtle and sophisticated techniques. However, there are several signs that can indicate the presence of a code injection attack. Unexpected behavior. if a system starts behaving unexpectedly, such as displaying error messages or generating unusual output, it could be a sign of a code injection attack. Increased system resource usage. Code injection attacks can consume significant system resources, leading to increased CPU or memory usage. Monitoring system performance can help identify such anomalies. Suspicious network traffic. Code injection attacks often involve communication with external servers or the transfer of data over the network. Monitoring network traffic can help identify suspicious patterns or connections. Log analysis. Analyzing system logs can provide valuable insights into potential code injection attacks. Look for unusual log entries, error messages, or unauthorized access attempts. Debugging code injection attacks. When a code injection attack is suspected, it is crucial to debug the system to identify the source of the vulnerability and mitigate the attack. Here are some debugging techniques and tools that can be used in a Linux environment. Source code analysis. Reviewing the source code of the affected application can help identify potential vulnerabilities that could be exploited for code injection attacks. Look for insecure input validation, improper use of system calls, or lack of input sanitization. Dynamic analysis. Dynamic analysis involves monitoring the behavior of a running application to identify any suspicious activities. Tools like strace and ltrace can be used to trace system calls and library calls, respectively, providing insights into the execution flow and potential code injection points. Input validation and sanitization. Implementing proper input validation and sanitization techniques can help prevent code injection attacks. Ensure that user input is properly validated, and use secure coding practices to sanitize input before using it in the application. Web application firewalls. Web application firewalls (WAFs) can help detect and prevent code injection attacks in web applications. WAFs analyze incoming requests and responses, looking for patterns that indicate potential code injection attempts. Intrusion detection systems. Intrusion detection systems (IDS) can monitor network traffic and system logs for signs of code injection attacks. IDS can detect patterns or signatures associated with known code injection techniques and raise alerts or take preventive actions. Security testing. Regular security testing, including penetration testing and vulnerability scanning, can help identify potential code injection vulnerabilities in a system. Tools like OWASP and Burp Suite can be used to simulate code injection attacks and identify weaknesses. Patching and updates. Keeping the system and its software up to date is crucial for preventing code injection attacks. Regularly apply security patches and updates to fix known vulnerabilities and protect against new attack vectors. Conclusion. Debugging code injection attacks in a Linux environment requires a combination of proactive measures and reactive techniques. By understanding the nature of code injection attacks and implementing proper security practices, you can reduce the risk of such attacks. Regular monitoring, analysis of system logs, and the use of debugging tools can help identify and mitigate code injection vulnerabilities, ensuring the security and integrity of your Linux system. 10.4 Debugging authentication issues. Authentication is a critical aspect of any system, ensuring that only authorized users can access resources and perform actions. However, authentication issues can arise in Linux systems, leading to security vulnerabilities and access problems. In this section, we will explore common authentication issues in Linux and discuss debugging techniques to identify and resolve them. Understanding authentication in Linux. Before diving into debugging authentication issues, it is essential to have a clear understanding of how authentication works in Linux. Linux systems typically use a combination of usernames and passwords to authenticate users. The authentication process involves verifying the user's credentials against a database, such as the etc. password and etc. shadow files. Linux also supports various authentication mechanisms, such as pluggable authentication modules (PAM), which provide a flexible framework for authentication. PAM allows system administrators to configure different authentication methods, such as passwords, smart cards, or biometrics, based on their specific requirements. Common authentication issues. Authentication issues can manifest in different ways, and it is crucial to identify the root cause to resolve them effectively. Here are some common authentication issues in Linux. 1. Incorrect passwords. One of the most common authentication issues is users entering incorrect passwords. This can happen due to typographical errors, forgotten passwords, or password synchronization problems. Debugging this issue involves verifying the password entered by the user and ensuring it matches the stored password in the authentication database. 2. User account lockouts. User account lockouts occur when a user exceeds the maximum number of failed login attempts, triggering a security measure to prevent further login attempts. This can happen due to brute force attacks or accidental mistyping of passwords. Debugging this issue involves checking the account lockout policies and unlocking the user account if necessary. 3. Expired or disabled accounts. Expired or disabled accounts can prevent users from authenticating successfully. User accounts may be disabled or expired due to security policies, account inactivity, or administrative actions. Debugging this issue involves checking the account status and enabling or extending the account validity if required. 4. Incorrect usernames. Sometimes, users may enter incorrect usernames during the authentication process. This can happen due to typographical errors or confusion with similar usernames. Debugging this issue involves verifying the username entered by the user and ensuring it exists in the authentication database. 5. Network connectivity issues. Authentication issues can also arise due to network connectivity problems. If the authentication server is unreachable or experiencing network issues, users may be unable to authenticate successfully. Debugging this issue involves checking the network connectivity between the client and the authentication server and resolving any network-related problems. Debugging authentication issues. When faced with authentication issues in Linux, it is essential to follow a systematic approach to identify and resolve the problem. Here are some debugging techniques to help you troubleshoot authentication issues effectively. 1. Review system logs. System logs, such as /var/log/auth.log or var/log secure, contain valuable information about authentication events and errors. Reviewing these logs can provide insights into the cause of authentication failures. Look for error messages, timestamps, and any relevant information that can help pinpoint the issue. 2. Verify user credentials. Ensure that the user is entering the correct username and password. If possible, try logging in with the user's credentials to verify their validity. If the issue persists, consider resetting the user's password and testing the authentication process again. 3. Check authentication configuration. Review the authentication configuration files, such as etc. pam, d*, to ensure they are correctly set up. Pay attention to any custom configurations or modifications that may impact the authentication process. Compare the configuration against a known working system if available. 4. Test authentication methods. If your Linux system supports multiple authentication methods, such as passwords, smart cards, or biometrics, test each method to identify if the issue is specific to a particular authentication method. This can help narrow down the problem and determine if it is related to a specific component or configuration. 5. Monitor network connectivity. If the authentication issue is suspected to be network-related, monitor the network connectivity between the client and the authentication server. Use tools like ping or traceroute to check for connectivity issues, packet loss, or network latency. Ensure that the authentication server is reachable and responsive. 6. Consult documentation and resources. Authentication issues can be complex, and it is often helpful to consult documentation and online resources specific to your Linux distribution or authentication mechanism. Check official documentation, forums, and community resources for troubleshooting guides, known issues, and solutions related to authentication problems. 7. Seek expert assistance. If you have exhausted all available debugging techniques and are still unable to resolve the authentication issue, consider seeking assistance from experienced Linux administrators or security professionals. They may have encountered similar issues before and can provide valuable insights and guidance. By following these debugging techniques and approaches, you can effectively identify and resolve authentication issues in Linux systems. Remember to document your troubleshooting steps and solutions for future reference and to share knowledge with others. 11. Debugging in production environments. 11.1 Debugging live systems. Debugging live systems in Linux can be a challenging task as it involves diagnosing and fixing issues in a production environment without disrupting the system's operation. This section will explore various techniques and best practices for debugging live systems in Linux. Understanding the challenges. Debugging live systems presents unique challenges compared to debugging in development or testing environments. In a live system, the primary goal is to identify and resolve issues without causing any downtime or disruption to the users. Here are some common challenges faced when debugging live systems. Limited access. In a live system, you may have limited access to the system due to security restrictions or the need to minimize disruption. This can make it difficult to gather necessary information for debugging. Real-time impact. Debugging live systems requires careful consideration as any changes made can have an immediate impact on the system's performance or availability. It is crucial to minimize the risk of introducing new issues while debugging. Lack of debugging tools. Live systems often have limited debugging tools installed to reduce the attack surface and improve performance. This means you may need to rely on existing tools or find creative ways to gather information for debugging. Reproducibility. Reproducing issues in a live system can be challenging, especially if they are intermittent or dependent on specific conditions. Without a reliable way to reproduce the problem, debugging becomes more complex. Strategies for debugging live systems. To effectively debug live systems in Linux, it is essential to follow a systematic approach and employ appropriate strategies. Here are some strategies to consider. Collecting system logs. System logs are a valuable source of information for debugging live systems. Configure the system to log relevant events and errors, and regularly monitor the logs for any anomalies. Tools like journalctl can help you retrieve and analyze system logs. Monitoring system performance. Monitoring the system's performance metrics can provide insights into potential issues. Tools like top, htop, and sar can help you monitor CPU, memory, disk, and network usage. By identifying abnormal patterns or bottlenecks, you can narrow down the scope of debugging. Using remote debugging tools. Remote debugging tools allow you to debug live systems without directly accessing them. Tools like strace, tcpdump, and netstack can help you analyze system calls, network traffic, and process information remotely. These tools are particularly useful when direct access to the system is limited. Analyzing core dumps. If a live system experiences a crash or segmentation fault, it may generate a core dump file. Analyzing core dumps with tools like GDB can provide valuable information about the state of the system at the time of the crash. This can help identify the root cause of the issue. Using dynamic tracing tools. Dynamic tracing tools like SystemTap and dtrace allow you to instrument the running system to gather detailed information about its behavior. These tools enable you to trace function calls, monitor system events, and capture performance data without disrupting the system's operation. Isolating components. When debugging live systems, it is often helpful to isolate specific components or subsystems to narrow down the scope of the issue. By selectively disabling or monitoring individual components, you can identify the source of the problem more efficiently. Testing in a controlled environment. If possible, create a controlled environment that closely resembles the live system for testing and debugging purposes. This can help you reproduce issues and experiment with potential solutions without impacting the production environment. Best practices for debugging live systems. To ensure a smooth and effective debugging process in live systems, consider the following best practices. Plan and communicate. Before starting the debugging process, create a plan outlining the steps you will take and the potential impact on the system. Communicate with stakeholders, including system administrators and users, to ensure everyone is aware of the debugging activities. Backup and restore. Before making any changes to a live system, ensure you have a reliable backup and restore mechanism in place. This allows you to roll back changes if unexpected issues arise during the debugging process. Document changes. Keep a detailed record of any changes made during the debugging process. This documentation will help you track your progress, share information with other team members, and revert changes if necessary. Test solutions in a staging environment. Whenever possible, test potential solutions in a staging environment that closely resembles the live system. This allows you to validate the effectiveness of the solution without impacting the production environment. Monitor the impact. Continuously monitor the system's performance and behavior during the debugging process. This helps you identify any unintended consequences or performance degradation caused by the debugging activities. Iterate and validate. Debugging live systems often requires an iterative approach. Validate each change or solution before moving on to the next step. This ensures that each modification is effective and does not introduce new issues. Document the debugging process. Maintain a comprehensive record of the debugging process, including the steps taken, the tools used, and the outcomes. This documentation will serve as a valuable resource for future reference and troubleshooting. By following these strategies and best practices, you can effectively debug live systems in Linux while minimizing disruption and ensuring the stability of the production environment. Remember to approach debugging with caution and prioritize the system's availability and performance throughout the process. 11.2 Debugging performance issues in production. Debugging performance issues in a production environment can be a challenging task. Unlike debugging issues in a development or testing environment, debugging performance problems in production requires careful consideration and a different approach. In this section, we will explore some techniques and strategies for debugging performance issues in a Linux production environment. Understanding performance issues. Before diving into debugging performance issues, it is important to have a clear understanding of what performance issues are and how they can impact your system. Performance issues can manifest in various ways, such as slow response times, high CPU or memory usage, excessive disk I/O, or network bottlenecks. These issues can significantly impact the overall user experience and can even lead to system failures. To effectively debug performance issues, it is crucial to have a solid understanding of the system architecture, the workload being executed, and the expected performance metrics. This knowledge will help you identify potential bottlenecks and focus your debugging efforts in the right direction. Monitoring and profiling tools. One of the first steps in debugging performance issues is to gather data about the system's behavior. This can be achieved through the use of monitoring and profiling tools. These tools provide valuable insights into the system's performance characteristics and can help identify potential bottlenecks. Some commonly used monitoring tools in Linux include top, htop, vmstat, sar, and nmon. These tools provide real-time information about CPU usage, memory usage, disk I/O, and network activity. By monitoring these metrics, you can identify any abnormal behavior or spikes in resource usage that may indicate a performance issue. Profiling tools, on the other hand, help you analyze the performance of specific components or functions within your application. Tools like perf, gprofessor, and Valgrind can be used to profile CPU usage, memory allocation, and function call traces. By profiling your application, you can identify performance bottlenecks at a more granular level and optimize the code accordingly. Analyzing performance data. Once you have collected performance data using monitoring and profiling tools, the next step is to analyze the data and identify the root cause of the performance issue. This can be a complex task, as performance issues can have multiple contributing factors. Start by looking for any anomalies or patterns in the performance data. Identify any spikes or dips in resource usage and correlate them with specific events or actions. This can help you narrow down the scope of your investigation and focus on the relevant areas. Next, analyze the performance data in relation to the workload being executed. Look for any correlations between the workload and the performance metrics. For example, if you notice high CPU usage during a specific operation, investigate that operation further to identify any potential inefficiencies or bottlenecks. It is also important to consider the impact of external factors on performance. Network latency, disk I/O contention, and resource contention with other applications can all contribute to performance issues. Analyze the performance data in the context of these external factors to get a holistic view of the system's behavior. Performance tuning and optimization. Once you have identified the root cause of the performance issue, the next step is to implement performance tuning and optimization techniques. This may involve modifying the code, optimizing database queries, adjusting system configurations, or scaling resources. When making changes to address performance issues, it is important to measure the impact of each change and validate its effectiveness. This can be done by repeating the performance analysis process and comparing the results before and after the changes. This iterative approach allows you to fine-tune the system and achieve optimal performance. Testing and validation. After implementing performance optimizations, it is crucial to thoroughly test and validate the changes in a controlled environment before deploying them to production. This ensures that the changes do not introduce new issues or regressions. Create a test environment that closely resembles the production environment and simulate realistic workloads. Measure the performance metrics and compare them with the baseline measurements taken before the optimizations. This will help you validate the effectiveness of the changes and ensure that the system performs as expected. Conclusion. Debugging performance issues in a Linux production environment requires a systematic approach and a deep understanding of the system's behavior. By using monitoring and profiling tools, analyzing performance data, implementing performance optimizations, and thoroughly testing the changes, you can effectively identify and resolve performance issues, ensuring that your system performs optimally in a production environment. 11.3 Debugging distributed systems. Distributed systems are complex software architectures that consist of multiple interconnected components running on different machines. Debugging issues in distributed systems can be challenging due to the distributed nature of the system and the potential for issues to arise from various components and interactions. In this section, we will explore some common debugging techniques and strategies for identifying and resolving issues in distributed systems running on Linux. Understanding the challenges of debugging distributed systems. Debugging distributed systems can be more challenging than debugging traditional monolithic applications. The main challenges arise from the following factors. Complexity. Distributed systems typically involve multiple components, each with its own set of dependencies and interactions. Identifying the root cause of an issue requires understanding the interactions between these components and their impact on the system as a whole. Concurrency. Distributed systems often rely on parallel processing and asynchronous communication between components. Debugging concurrency-related issues, such as race conditions and deadlocks, requires specialized techniques and tools. Network communication. Communication between distributed components often occurs over a network, introducing additional points of failure and potential issues. Debugging network-related problems requires analyzing network traffic, identifying bottlenecks, and ensuring proper configuration and connectivity. Distributed data. Distributed systems often rely on distributed data storage and replication. Debugging issues related to data consistency, replication, and synchronization requires understanding the underlying data model and the mechanisms used for data distribution. Debugging techniques for distributed systems. When debugging distributed systems, it is important to adopt a systematic approach and leverage appropriate tools and techniques. Here are some techniques that can help in the debugging process. Logging and tracing. Instrument your distributed system with extensive logging and tracing capabilities. Log messages and trace data can provide valuable insights into the system's behavior and help identify the root cause of issues. Use centralized logging solutions to aggregate and analyze logs from multiple components. Distributed tracing. Distributed tracing allows you to trace requests as they flow through the various components of a distributed system. By correlating trace data from different components, you can gain a holistic view of the request's journey and identify bottlenecks or failures. Monitoring and metrics. Implement comprehensive monitoring and metrics collection in your distributed system. Monitor key performance indicators (KPIs) and collect metrics related to resource utilization, latency, throughput, and error rates. Analyzing these metrics can help identify performance bottlenecks and anomalies. Fault injection. Introduce controlled faults and failures into your distributed system to simulate real-world scenarios and test its resilience. By intentionally triggering failures, you can observe how the system behaves and identify potential weaknesses or failure points. Debugging tools. Utilize debugging tools specifically designed for distributed systems. These tools provide features such as distributed breakpoints, distributed stack traces, and the ability to inspect the state of multiple components simultaneously. Examples of such tools include Dapper, Zipkin, and Jaeger. Reproducibility. Whenever possible, try to reproduce the issue in a controlled environment. Isolate the problematic component or interaction and create a minimal test case that reproduces the issue. This will help in narrowing down the root cause and facilitate the debugging process. Collaboration and communication. Debugging distributed systems often requires collaboration between different teams or individuals responsible for different components. Establish effective communication channels and share relevant information, such as logs, traces, and metrics, to facilitate the debugging process. Debugging distributed systems in production. Debugging distributed systems in production environments requires additional considerations due to the potential impact on live systems. Here are some best practices for debugging distributed systems in production. Incremental deployments. When deploying changes or updates to a distributed system, consider using incremental deployments. This allows you to gradually roll out changes and monitor the impact on the system. If issues arise, you can quickly roll back the changes and minimize the impact on users. Feature flags. Use feature flags to enable or disable specific features or components of your distributed system. This allows you to selectively enable or disable functionality in production, making it easier to isolate and debug issues related to specific components or features. Canary releases. Deploy new versions of your distributed system to a small subset of users or machines before rolling out to the entire system. This allows you to gather feedback and identify any issues or performance problems before affecting the entire user base. A/B testing. Conduct A/B testing to compare the performance and behavior of different versions or configurations of your distributed system. By running multiple versions simultaneously and comparing the results, you can identify any discrepancies or issues that may arise. Rolling logs and metrics. Ensure that your distributed system's logging and metrics collection mechanisms are designed to handle high volumes of data. Implement log rotation and aggregation strategies to prevent overwhelming the system with excessive log data. Graceful degradation. Implement graceful degradation mechanisms in your distributed system to handle failures or performance degradation gracefully. This can involve fallback mechanisms, circuit breakers, or load shedding strategies to ensure that the system remains operational even in the presence of issues. By following these techniques and best practices, you can effectively debug and resolve issues in distributed systems running on Linux. Remember to adopt a systematic approach, leverage appropriate tools, and collaborate with other teams or individuals involved in the system's development and maintenance. 11.4 Debugging cloud-based applications. Cloud-based applications have become increasingly popular due to their scalability, flexibility, and cost-effectiveness. However, debugging these applications can be challenging due to their distributed nature and reliance on various cloud services. In this section, we will explore some common debugging techniques and tools that can help you troubleshoot issues in cloud-based applications running on Linux. Understanding the challenges of debugging cloud-based applications. Debugging cloud-based applications presents unique challenges compared to traditional on-premises applications. Here are some of the key challenges you may encounter. Distributed architecture. Cloud-based applications often consist of multiple services running on different servers or even different cloud providers. This distributed architecture can make it difficult to trace the flow of data and identify the root cause of issues. Limited access. Cloud providers typically restrict direct access to the underlying infrastructure, making it harder to debug applications. You may have limited visibility into the network, storage, and other resources that your application relies on. Dynamic environment. Cloud environments are highly dynamic, with resources being provisioned and deprovisioned on demand. This dynamic nature can introduce new variables and make it challenging to reproduce and debug issues consistently. Third-party services. Cloud-based applications often rely on various third-party services, such as databases, message queues, and authentication providers. Debugging issues that involve these services requires understanding their APIs and integration points. Debugging techniques for cloud-based applications. To effectively debug cloud-based applications, you need to adopt a systematic approach that takes into account the challenges mentioned above. Here are some techniques you can use. Logging and monitoring. Implement comprehensive logging and monitoring in your application. Cloud providers offer various logging and monitoring services that can help you track the behavior of your application and identify potential issues. Analyzing logs and metrics can provide valuable insights into the performance and behavior of your application. Distributed tracing. Distributed tracing allows you to trace the flow of requests across different services and identify bottlenecks or failures. By instrumenting your code with tracing libraries, you can collect and analyze trace data to understand the interactions between different components of your application. Error tracking. Utilize error tracking tools to capture and analyze application errors. These tools can help you identify recurring errors, track error trends, and prioritize debugging efforts. They often provide detailed error reports, including stack traces and contextual information, to aid in troubleshooting. Remote debugging. Some cloud providers offer remote debugging capabilities that allow you to attach a debugger to your running application instances. This enables you to inspect variables, set breakpoints, and step through the code to identify and fix issues in real time. Load testing. Simulate high loads on your application to identify performance bottlenecks and scalability issues. Load testing tools can help you measure the response time, throughput, and resource utilization of your application under different load conditions. By analyzing the results, you can optimize your application's performance and identify potential issues. Code review and pair programming. Collaborate with your team members through code reviews and pair programming sessions. This can help identify potential issues early in the development process and improve the overall quality of your code. Having multiple sets of eyes on the code can also help catch subtle bugs and improve the effectiveness of debugging efforts. Debugging tools for cloud-based applications. Several debugging tools can assist you in troubleshooting cloud-based applications running on Linux. Here are some commonly used tools. Cloud provider tools. Cloud providers offer various tools and services that can aid in debugging. For example, AWS CloudWatch provides monitoring and logging services, while Google Cloud Platform offers Stackdriver for logging, monitoring, and debugging. Distributed tracing tools. Tools like Jaeger and Zipkin enable distributed tracing by collecting and visualizing trace data. These tools allow you to understand the flow of requests across different services and identify performance bottlenecks. Error tracking tools. Sentry and Rollbar are popular error tracking tools that capture and report application errors. They provide detailed error reports, including stack traces and contextual information, to help you diagnose and fix issues. Load testing tools. Tools like Apache JMeter and Locust can simulate high loads on your application and measure its performance under different conditions. These tools help you identify performance bottlenecks and ensure your application can handle the expected load. Remote debugging tools. Some cloud providers, such as AWS and Azure, offer remote debugging capabilities for Linux-based applications. These tools allow you to attach a debugger to your running instances and debug them in real time. IDEs and debuggers. Integrated development environments IDEs like Visual Studio Code and JetBrains IntelliJ IDEA provide powerful debugging capabilities for cloud-based applications. They support remote debugging, breakpoints, variable inspection, and other essential debugging features. Conclusion. Debugging cloud-based applications running on Linux requires a systematic approach and the use of appropriate tools. By implementing comprehensive logging, monitoring, and distributed tracing, you can gain valuable insights into the behavior of your application. Additionally, utilizing error tracking, load testing, and remote debugging tools can help you identify and resolve issues efficiently. Remember to leverage the collaboration of your team members through code reviews and pair programming sessions to improve the overall quality of your code. With the right techniques and tools, you can effectively debug cloud-based applications and ensure their smooth operation in production environments. 12. Debugging tips and best practices. 12.1 Effective debugging strategies. Debugging is an essential skill for any Linux developer or system administrator. It involves identifying and fixing issues in software or systems to ensure they function correctly. Effective debugging strategies can significantly improve the efficiency and accuracy of the debugging process. In this section, we will explore some key strategies that can help you become a more effective debugger in a Linux environment. Understand the problem. Before diving into the debugging process, it is crucial to have a clear understanding of the problem at hand. Take the time to gather as much information as possible about the issue, including the symptoms, error messages, and any relevant logs or documentation. This initial investigation will provide valuable insights into the root cause of the problem and guide your debugging efforts. Reproduce the issue. One of the most effective ways to debug a problem is to reproduce it consistently. By replicating the issue, you can observe its behavior and analyze the underlying causes more effectively. This may involve creating a test environment that closely resembles the production environment or using specific inputs to trigger the problem. Reproducing the issue will allow you to isolate and analyze the problematic code or configuration. Divide and conquer. When faced with a complex problem, it can be overwhelming to debug the entire system or application at once. Instead, break down the problem into smaller, more manageable parts. By dividing the system into components or modules, you can focus your debugging efforts on specific areas, making it easier to identify the root cause. This approach also helps in isolating the problem and prevents unnecessary changes to unaffected parts of the system. Use logging and debugging tools. Logging and debugging tools are invaluable resources for Linux debugging. By strategically placing log statements or using debugging tools like GDB, SystemTap, or dtrace, you can gather valuable information about the system's behavior during runtime. These tools allow you to trace the execution flow, inspect variables, and identify potential issues. Leveraging the power of logging and debugging tools can significantly speed up the debugging process and provide valuable insights into the problem. Analyze error messages and stack traces. Error messages and stack traces are valuable clues that can help you pinpoint the root cause of a problem. When an error occurs, carefully analyze the error message to understand the nature of the issue. Look for specific error codes, file paths, or function names that can provide insights into the problem. Stack traces, which show the sequence of function calls leading to the error, can also be instrumental in identifying the problematic code or configuration. Test and validate hypotheses. Debugging often involves forming hypotheses about the root cause of the problem and testing them systematically. Once you have identified a potential cause, design experiments or tests to validate your hypothesis. This may involve modifying code, configuration settings, or inputs to observe the impact on the system's behavior. By testing and validating hypotheses, you can narrow down the possible causes and focus your debugging efforts more effectively. Collaborate and seek help. Debugging can be a challenging task, and it is often beneficial to seek help from others. Collaborating with colleagues, participating in online forums, or seeking assistance from the open-source community can provide fresh perspectives and insights into the problem. Explaining the issue to someone else can also help you clarify your thoughts and identify potential blind spots. Don't hesitate to reach out for help when needed. Document and share findings. As you progress through the debugging process, it is essential to document your findings and share them with others. Keeping detailed notes about the steps you have taken, the hypotheses you have tested, and the results you have obtained will not only help you track your progress but also serve as a valuable resource for future debugging sessions. Sharing your findings with colleagues or the wider community can also contribute to collective knowledge and help others facing similar issues. Practice and learn from experience. Debugging is a skill that improves with practice and experience. The more you debug, the better you become at identifying patterns, understanding system behavior, and finding solutions. Take the time to reflect on your debugging sessions, analyze what worked well, and learn from any mistakes or challenges you encountered. Embrace a growth mindset and continuously seek opportunities to enhance your debugging skills. In conclusion, effective debugging strategies are essential for successfully resolving issues in a Linux environment. By understanding the problem, reproducing the issue, dividing and conquering, using logging and debugging tools, analyzing error messages and stack traces, testing hypotheses, collaborating, documenting findings, and practicing regularly, you can become a more efficient and skilled debugger. Remember that debugging is not just about fixing problems but also about learning and improving your understanding of the system. 12.2 Debugging Tools and Techniques. Debugging is an essential part of the software development process. It helps identify and fix issues in programs, ensuring they run smoothly and efficiently. In Linux, there are several powerful debugging tools and techniques available that can aid developers in finding and resolving bugs. In this section, we will explore some of the commonly used debugging tools and techniques in Linux. 12.2.1 GDB New Debugger. GDB, or the GNU Debugger, is a widely used command-line debugger for Linux and other Unix-like systems. It allows developers to analyze and debug programs written in various programming languages, including C, C++, and Fortran. GDB provides a range of features, such as breakpoints, watchpoints, and stepping through code, to help identify and fix bugs. One of the key features of GDB is its ability to provide detailed information about the program's execution, including the values of variables in the call stack. This information can be invaluable in understanding the program's behavior and identifying the root cause of bugs. GDB also supports remote debugging, allowing developers to debug programs running on remote machines. 12.2.2 Valgrind. Valgrind is a powerful debugging and profiling tool for Linux. It is designed to detect memory leaks, buffer overflows, and other memory-related errors in programs. Valgrind works by running the program in a virtual environment and monitoring its memory usage. It can detect issues such as accessing uninitialized memory, using freed memory, and reading and writing beyond the bounds of allocated memory. In addition to memory debugging, Valgrind also provides tools for profiling and performance analysis. It can generate detailed reports on the program's memory usage, cache behavior, and CPU performance. These reports can help developers optimize their code and improve overall program performance. 12.2.3 Strace. Strace is a command-line tool that allows developers to trace system calls and signals made by a program. It can be used to monitor the interactions between a program and the operating system, providing valuable insights into its behavior. Strace can help identify issues such as file access errors, permission problems, and incorrect system call usage. By tracing system calls, Strace can also help pinpoint performance bottlenecks in a program. It can show the time taken by each system call, allowing developers to identify areas of the code that may need optimization. Strace is particularly useful for debugging system-level issues and understanding how programs interact with the underlying operating system. 12.2.4 ltrace. ltrace is a debugging tool that allows developers to trace library calls made by a program. It can be used to monitor the interactions between a program and the shared libraries it depends on. ltrace can help identify issues such as incorrect library usage, missing library dependencies, and compatibility problems. By tracing library calls, ltrace can provide valuable insights into a program's behavior and help identify the root cause of bugs. It can show the arguments passed to library functions and the values returned by them. ltrace is particularly useful for debugging issues related to dynamic linking and library dependencies. 12.2.5 SystemTap. SystemTap is a powerful tracing and probing tool for Linux. It allows developers to monitor and trace the behavior of the Linux kernel and user space programs in real time. SystemTap provides a scripting language that allows developers to write custom probes and trace points to capture specific events and data. With SystemTap, developers can trace system calls, function calls, and other events in the kernel and user space programs. It can help identify performance bottlenecks, resource usage patterns, and other system-level issues. SystemTap is particularly useful for debugging complex systems and analyzing the interactions between different components. 12.2.6 Perf. Perf is a performance analysis tool for Linux. It provides a wide range of features for profiling and analyzing the performance of programs. Perf can collect detailed information about CPU usage, cache behavior, memory access patterns, and other performance-related metrics. With Perf, developers can identify performance bottlenecks, optimize code, and improve overall program performance. Perf supports various profiling modes, including CPU profiling, memory profiling, and event-based profiling. It can generate detailed reports and visualizations to help developers understand and analyze the performance of their programs. 12.2.7 Other tools and techniques. In addition to the above-mentioned tools, there are several other debugging tools and techniques available in Linux. Some of these include GDB Server, allows remote debugging of programs running on a target machine. Address Sanitizer, a runtime tool that detects memory bugs, such as buffer overflows and use after free errors. Core Dumps, allows developers to analyze the state of a crashed program by generating a core dump file. Log files, logging can be a valuable debugging technique, providing insights into the program's execution and behavior. Debugging symbols, including debugging symbols in the compiled program can provide more meaningful stack traces and error messages. These tools and techniques, when used effectively, can greatly simplify the debugging process and help developers identify and fix bugs more efficiently. It is important for developers to familiarize themselves with these tools and techniques and incorporate them into their debugging workflow. 12.3 Debugging Workflow and Process. Debugging is an essential part of the software development process. It helps identify and fix issues in the code, ensuring that the software functions as intended. In Linux, debugging can be a complex task due to the diverse range of applications and system-level components. To effectively debug in a Linux environment, it is important to follow a structured workflow and process. This section will outline a general debugging workflow and provide some best practices to help you streamline your debugging process. Understanding the problem. The first step in the debugging process is to understand the problem at hand. This involves gathering information about the issue, reproducing it if possible, and analyzing any error messages or logs. It is important to have a clear understanding of the expected behavior and the actual behavior of the software. This will help you narrow down the scope of the problem and identify potential root causes. Reproducing the issue. Once you have a clear understanding of the problem, the next step is to reproduce the issue. Reproducing the issue is crucial as it allows you to observe the problem in a controlled environment, making it easier to debug. This may involve running specific test cases, providing certain inputs, or following a specific sequence of steps. By reproducing the issue, you can isolate the problem and focus your debugging efforts on the relevant code or system component. Analyzing the code. After reproducing the issue, it is time to analyze the code. This involves examining the relevant sections of the code to identify any potential bugs or issues. It is important to review the code carefully, paying attention to details such as variable assignments, function calls, and control flow. Debugging tools like GDB, SystemTap, or dtrace can be used to step through the code, set breakpoints, and inspect variables at runtime. By analyzing the code, you can identify the root cause of the problem and devise a solution. Fixing the issue. Once the root cause of the problem has been identified, the next step is to fix the issue. This may involve making changes to the code, modifying system configurations, or applying patches. It is important to test the fix thoroughly to ensure that it resolves the problem without introducing new issues. Automated tests, unit tests, and regression tests can be used to validate the fix and ensure that the software functions as expected. Testing and verification. After fixing the issue, it is important to perform thorough testing and verification. This involves running various test cases, including both positive and negative scenarios, to ensure that the problem has been resolved. It is also important to test the software in different environments and configurations to identify any potential compatibility issues. Additionally, it is a good practice to involve other team members or stakeholders in the testing process to get their feedback and ensure that the fix meets the desired requirements. Documentation and communication. Throughout the debugging process, it is important to maintain proper documentation. This includes documenting the steps taken to reproduce the issue, the analysis of the code, the fix implemented, and the testing and verification results. Proper documentation helps in knowledge sharing, enables future reference, and facilitates collaboration with other team members. It is also important to communicate the debugging process and the fix to other stakeholders, such as project managers or customers, to keep them informed about the progress and ensure transparency. Continuous improvement. Debugging is an iterative process, and there is always room for improvement. It is important to learn from each debugging experience and incorporate the lessons learned into future projects. This can involve improving the testing process, enhancing the code review process, or adopting new debugging tools and techniques. Regularly reviewing and refining the debugging workflow and process can help streamline the debugging efforts and improve the overall software quality. In conclusion, debugging in a Linux environment requires a structured workflow and process. By following a systematic approach, understanding the problem, reproducing the issue, analyzing the code, fixing the issue, testing and verifying the fix, documenting the process, and continuously improving, you can effectively debug software in a Linux environment. Remember that debugging is not just about fixing issues, it is also about learning and improving the software development process. 12.4 Debugging Documentation and Resources. When it comes to debugging in Linux, having access to reliable documentation and resources is crucial. Linux is a widely used operating system, and as a result, there are numerous sources of information available to help you troubleshoot and resolve issues. In this section, we will explore some of the essential debugging documentation and resources that can assist you in your debugging journey. 12.4.1 Linux Man Pages. One of the most valuable resources for Linux debugging is the Linux Man Pages. The man pages, short for manual pages, provide detailed documentation on various Linux commands, system calls, library functions, and configuration files. These pages offer comprehensive explanations, usage examples, and often include troubleshooting tips. To access the man pages, you can use the man command followed by the name of the command or function you want to learn more about. For example, to view the manual page for the ls command, you would run man ls. The man pages are organized into sections, and you can specify the section number to narrow down your search. For instance, man2open will display the manual page for the open system call. 12.4.2 Online Forums and Communities. Online forums and communities dedicated to Linux and debugging are excellent resources for getting help and advice from experienced users and professionals. Websites like Stack Overflow, linuxquestions.org, and Reddit's Linux communities provide platforms for asking questions, sharing knowledge, and discussing Linux-related topics. When seeking assistance on these platforms, it's essential to provide detailed information about the issue you're facing, including any error messages, relevant code snippets, and steps you've already taken to troubleshoot the problem. Be respectful and patient when interacting with others, and remember to follow any community guidelines or rules. 12.4.3 Linux Debugging Tools Documentation. Linux offers a wide range of debugging tools, each with its own set of features and capabilities. Understanding how to use these tools effectively requires referring to their respective documentation. Most Linux debugging tools have comprehensive manuals or online documentation that provide detailed explanations of their usage, command options, and examples. For example, the GNU Debugger (GDB) has extensive documentation available on the official GDB website. The documentation covers topics such as installing GDB, basic and advanced debugging techniques, remote debugging, and integrating GDB with other tools. Similarly, SystemTap and dtrace, two powerful tracing and debugging tools, have their own documentation that explains how to write scripts, analyze system performance, and debug specific issues. 12.4.4 Linux Kernel Documentation. If you're dealing with kernel-level debugging or issues related to device drivers, the Linux kernel documentation is an invaluable resource. The Linux kernel source code includes a vast collection of documentation files that cover various aspects of the kernel, including debugging and troubleshooting. The kernel documentation provides insights into kernel internals, debugging techniques, kernel configuration options, and device driver development. It also includes information on how to interpret kernel error messages, use kernel debugging tools, and analyze kernel crashes. You can find the kernel documentation in the documentation directory of the kernel source code or access it online through the official Linux kernel website. 12.4.5 Linux Distribution Documentation. Each Linux distribution has its own set of documentation that covers specific aspects of the distribution, including debugging and troubleshooting. These resources often include installation guides, system administration manuals, and troubleshooting guides tailored to the distribution's unique features and configurations. For example, the Ubuntu documentation provides detailed information on various topics, including debugging common issues, configuring system services, and troubleshooting hardware problems. Similarly, the Red Hat Enterprise Linux documentation offers comprehensive guides on debugging system-level issues, managing system performance, and resolving security vulnerabilities. 12.4.6 Official Websites and Blogs. Official websites and blogs maintained by Linux distributions, software projects, and individual developers can be excellent sources of debugging information. These websites often publish articles, tutorials, and guides that cover specific debugging scenarios, best practices, and tips for troubleshooting common issues. For example, the official websites of popular Linux distributions like Ubuntu, Fedora, and Debian have dedicated sections for documentation and support. These sections provide resources such as knowledge bases, forums, and blogs that can help you find solutions to your debugging problems. Additionally, many software projects and individual developers maintain blogs where they share their experiences, insights, and debugging techniques. 12.4.7 Books and Online Courses. Books and online courses focused on Linux debugging can provide in-depth knowledge and guidance on various debugging techniques and tools. These resources often cover a wide range of topics, from basic debugging concepts to advanced debugging strategies for specific scenarios. Some recommended books on Linux debugging include The Art of Debugging with GDB, DDD, and Eclipse, by Norman Matloff and Peter J. Salzman, Linux Debugging and Performance Tuning, by Steve Best, and Linux Debugging, by Christopher Paul. Online platforms like Udemy, Coursera, and Linux Foundation Training offer courses on Linux debugging that can provide structured learning experiences and hands-on practice. 12.4.8 Source Code and Open Source Projects. Examining the source code of open source projects can be an effective way to learn about debugging techniques and gain insights into how different software components work. Many open source projects host their code repositories on platforms like GitHub, GitLab, and Bitbucket, making it easy to access and explore the source code. By studying the source code of projects related to your debugging problem, you can understand how developers handle similar issues and apply their solutions to your own code. Additionally, open source projects often have issue trackers and discussion forums where you can find information about known bugs, workarounds, and debugging tips. In conclusion, having access to reliable documentation and resources is essential for effective debugging in Linux. The Linux man pages, online forums and communities, debugging tools documentation, Linux kernel documentation, distribution documentation, official websites and blogs, books and online courses, and source code of open source projects are all valuable sources of information that can help you navigate and resolve debugging challenges in Linux.